Hello there, and welcome back to Sleep Philosopher. I'm so glad you've found your way here tonight. Come, settle in. Pull the covers a little closer, let your shoulders drop, and allow the quiet to hold you. Tonight, we are going to do something a little unusual. We are going to look at mathematics, not the kind that lives in textbooks or on chalkboards, but the kind that hides in the deep silent architecture of everything that exists. Numbers that behave in ways they shouldn't, patterns that appear where no one planted them, truths that are real but can never be proven. This is not a lecture. This is a slow walk through some of the strangest corridors the human mind has ever wandered into. You don't need to understand everything. You only need to listen. So take a long, gentle breath. Let your thoughts grow soft and quiet, and let us begin. Chapter 1. The universe speaks in numbers, but nobody taught it to. Hello, and welcome to the first stop on tonight's quiet journey, before we lose ourselves in the strange and winding corridors of specific mathematical mysteries. Let us begin at the very beginning, not with a formula, not with an equation, but with a feeling that most mathematicians, at some point in their lives, have quietly admitted to experiencing. The feeling that mathematics is not something we invented, that it was already here, waiting, that we simply found it. This idea, simple as it sounds, is one of the most divisive and deeply unsettling questions in all of human intellectual history. And it begins with a question so fundamental that it is almost embarrassing to ask out loud. Where does mathematics come from? Take a moment with that. Not where do numbers come from, in the sense of who first scratched symbols into clay tablets, or which civilization first developed a counting system. That history is fascinating, but it is not what we are asking tonight. The question is deeper, more personal, more strange. Did human beings create mathematics the way we create music or painting or language, as a beautiful, elaborate invention of the mind? Or did we discover it? The way an explorer discovers a coastline that existed long before any ship ever sailed toward it. This debate has a name in philosophy. It is called the question of mathematical ontology, the study of what mathematics actually is, and whether it exists independently of the minds that think about it. On one side of this debate stand the Platonists, named after the ancient Greek philosopher Plato, who believed that abstract objects, numbers, geometric forms, mathematical relationships exist in a realm of their own, outside of time, outside of space, outside of the physical universe entirely. On the other side stand the formalists and the constructivists, who argue that mathematics is a language, a set of rules that human beings agreed upon, a game we invented and then became very, very good at playing. For most of history, this felt like a purely philosophical argument, the kind that clever people have over wine, with no practical consequences either way. But then something began to happen that made the question feel far less abstract, far less comfortable. Mathematicians and physicists, working independently in completely different fields, kept discovering the same unsettling thing. Mathematics that had been invented purely for its own sake, with no connection to the physical world whatsoever, kept turning out to describe physical reality with breathtaking, almost eerie precision. Let us take the most famous example, the number pi. You know it, at least a little. It is approximately 3.14159, and it goes on forever without repeating. Pi is defined as the ratio of a circle's circumference to its diameter. Simple enough. A geometric fact about circles. And yet pi appears in places that have nothing to do with circles. It appears in the mathematics of probability, in a beautiful result called the Basel problem, where adding the reciprocals of all the perfect squares produces an answer involving pi, for reasons that feel almost miraculous. It appears in the equations governing waves, in the behavior of pendulums, in the statistics of random processes, in the quantum mechanical equations that describe the behavior of electrons. Nobody put pi there. Nobody designed the universe to use it. And yet, there it is, turning up again and again, like a signature left behind by something we cannot name. And pi is not alone. The number e, the base of natural logarithms, appears throughout the mathematics of growth and decay, in population dynamics, in compound interest, in the way electrical circuits charge and discharge, in the probability distributions that govern everything from exam scores to the distribution of stars. The imaginary number I, defined as the square root of -1, a number that seems, on its face, to be a purely fictional construct invented to solve equations that have no real solutions, turns out to be absolutely essential to quantum mechanics. Without imaginary numbers, we cannot write down the equations that describe how matter behaves at the subatomic level. A number that appears to be make-believe is, in a very real sense, the language in which the universe describes itself at its most fundamental layer. It was this pattern, this relentless, inexplicable pattern of abstract mathematics turning out to describe concrete reality that led the physicist Eugene Wigner in 1960 to write one of the most quietly unsettling essays in the history of science. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. In it, he marveled at the fact that mathematical structures developed with no application in mind by mathematicians pursuing pure abstract beauty kept being discovered later to be precisely what physics needed. He called it a gift we neither understand nor deserve. He was not being poetic. He was genuinely disturbed. And here is why that disturbance matters. If mathematics were simply a language we invented, a set of symbols and rules that we constructed to describe the world, then its usefulness would make perfect sense. Of course, the map fits the territory. We drew the map to fit. But if mathematicians are regularly inventing purely abstract structures with no reference to physical reality, and those structures later turn out to describe physical reality with perfect accuracy, then the map is fitting a territory it was never drawn for. That should not be possible, and yet it keeps happening. Some thinkers have taken this observation to its logical extreme. The physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, the idea that the universe is not merely described by mathematics, but that it is mathematics, that physical reality and mathematical reality are the same thing. That the reason the universe obeys mathematical laws is not because mathematics is a useful tool we apply to it from the outside, but because the universe is, at its core, a mathematical structure, and we, conscious, wondering, breathing beings, are patterns within that structure, complex enough to have become aware of the equations that compose us. Pause here for just a moment. Let that image settle. You are made of atoms. Those atoms obey laws. Those laws are written in the language of mathematics. And you, somehow, are capable of reading that language, of finding it beautiful, of being unsettled by it in the quiet hours of the night. The universe wrote a story in numbers, and then, after 13 billion years, produced creatures capable of reading it and wondering what it means. Whether mathematics was invented or discovered may be a question without a final answer, but the feeling it produces, that quiet, vertiginous sense that the numbers were here before we were, that they will be here after we are gone, that they exist in some form that transcends the physical matter of the brains that think about them. That feeling is not nothing. Many of the greatest mathematical minds in history have felt it. Plato built a philosophy around it. Cantor was overwhelmed by it. Ramanujan described it as divine, and even the most rigorous, skeptical, empirically minded scientists have paused at some point and admitted that the relationship between mathematics and reality is stranger than it has any right to be. Perhaps we invented the symbols and discovered what they pointed to. Perhaps the act of doing mathematics is the universe turning its own gaze upon itself, using the minds it produced to read the patterns it contains. Perhaps there is no difference between invention and discovery at the deepest level. Perhaps the most honest answer is simply this: we do not know, and the not knowing is where tonight's journey begins. Take a slow, deep breath. Let the questions stay open. We are in no hurry here, because as strange as this opening idea is, it is only the first door, and the corridor beyond it goes very, very deep. Chapter 2, Gödel's Incompleteness, the theorem that broke mathematics. There is a particular kind of vertigo that comes not from standing at the edge of a great height, but from standing at the edge of a great idea. The kind of vertigo that arrives quietly, without warning, when you realize that something you assumed was solid, something you built your entire understanding upon, has a crack running through its very foundation. Not a crack that can be repaired, not a flaw that more knowledge or more effort will eventually fill in, but a crack that is, by its very nature, permanent, structural, irreducible. In 1931, a young Austrian mathematician named Kurt Gödel handed that feeling to the entire world of mathematics. He was 25 years old. He was soft-spoken, deeply private, and by most accounts, quietly brilliant in a way that made other brilliant people feel uneasy. And in that year, he published a proof that did something no one had thought possible, and that many people, upon first encountering it, refused to believe. He proved that mathematics, the one discipline humanity had always trusted as the gold standard of certainty, the unshakable foundation of logical truth, was fundamentally, irreparably incomplete. To understand what that means and why it matters so deeply, we need to travel back a little further, back to the turn of the 20th century, when mathematics was in the middle of what its practitioners believed was a golden age. The great German mathematician David Hilbert had proposed an ambitious program, a project to place all of mathematics on an absolutely secure, unassailable foundation. The idea was to identify a complete set of axioms, basic, self-evident truths that everyone could agree upon, and then from those axioms alone, using pure logic, to derive every true mathematical statement that had ever been made or ever could be made, a perfect, complete, consistent system, a mathematical universe with no gaps, no shadows, no unanswerable questions, everything either provable or disprovable, nothing left to chance or intuition. It was a beautiful dream, and for a while it seemed achievable. The philosophers Bertrand Russell and Alfred North Whitehead spent years constructing a monumental work called Principia Mathematica, an attempt to derive all of mathematics from pure logical axioms. The project took decades. The first volume alone ran to hundreds of pages before it managed to rigorously prove that 1 + 1 = 2. But the ambition was real, and the mathematical community rallied around it. Surely with enough care and enough rigor the edifice could be completed. And then Gödel read it and saw something no one else had seen. What Gödel realized, and what he then proved with absolute mathematical rigor, was that any formal system powerful enough to describe basic arithmetic will inevitably contain statements that are true, but that cannot be proven within the system itself. Not statements that are merely difficult to prove, not statements that we haven't gotten around to proving yet, statements that are genuinely, permanently beyond the reach of the system's own rules, even though they are true. The system cannot be both complete and consistent. You can have one or the other. You cannot have both. The way Gödel demonstrated this is one of the most elegant and unsettling maneuvers in the history of human thought. He found a way to make mathematics talk about itself. Using a clever encoding technique, now called Gödel numbering, he assigned a unique number to every symbol, every formula, and every proof in a mathematical system. This meant that statements about numbers could secretly be statements about the system itself. And using this technique, he constructed a mathematical statement that, when decoded, said something remarkably simple and deeply strange. It said, in effect, this statement cannot be proven within this system. Now consider what that means. If the statement is false, then it can be proven, but that would mean the system proves something false, which means the system is inconsistent, which destroys everything. If the statement is true, then it cannot be proven, which means the system is incomplete. There is no third option, no escape route, no clever workaround. The system is either inconsistent or incomplete. And no amount of adding new axioms or expanding the rules can permanently fix this, because any new, more powerful system will simply generate its own version. This is Gödel's first incompleteness theorem, and if that alone weren't enough, he followed it almost immediately with a second theorem that struck an even deeper blow. His second incompleteness theorem states that no consistent formal system can prove its own consistency. In other words, mathematics cannot pull itself up by its own bootstraps. It cannot look inward, examine its own foundations, and confirm that everything is sound. The only way to prove that a mathematical system is consistent is to use a more powerful system, which itself cannot prove its own consistency, which requires a still more powerful system, and so on, without end, without resolution, without ground. Hilbert's dream was over. The perfect, complete, self-verifying mathematical universe was not merely unfinished, it was impossible. Take a moment here, let that settle in the quiet. The implications of Gödel's theorems reach far beyond mathematics itself, if you believe, as many philosophers do, that the human mind is in some sense a formal system. That thinking is a kind of computation, operating according to rules. Then Gödel's theorems suggest that the human mind too has truths it can recognize but never prove. Intuitions that outrun the formal systems we use to verify them, knowledge that exists at the edges of our logical reach, visible but untouchable. Some philosophers, most notably the mathematician and physicist Roger Penrose, have argued that Gödel's incompleteness theorems actually prove that the human mind is not a formal system, that our ability to recognize Gödelian truths as true demonstrates something beyond mere computation. Others disagree. The debate continues, unresolved, as perhaps it must. But there is something more personal in Gödel's story that deserves a moment of quiet reflection. The man who proved that all systems have limits was, in his own life, a person consumed by a desperate need for certainty. He was famously paranoid, deeply anxious, obsessed with the possibility that people were trying to poison him in his later years. He refused to eat food that had not been prepared by his wife, Adele. When Adele was hospitalized in 1977, Gödel stopped eating almost entirely. He died of starvation, his body weighing less than 30 kilograms, in January of 1978. The man who showed the world that certainty has fundamental limits spent his final years in a desperate and ultimately fatal search for it. What Gödel left us with is not despair, though it can feel that way at first. What he left us with is something more honest, and in its honesty, more beautiful. He left us with the knowledge that truth is larger than proof, that there are real, genuine facts about mathematics, and perhaps about reality, that exist beyond the reach of any system we can construct to describe them. The universe is not a closed book. It is an open one, with pages that no finite reader can ever fully turn. And in a strange way, that is a gift, because it means that the horizon of mathematical truth is not a wall, it is a window, and beyond it, always, there is more. Breathe slowly. Let the incompleteness be something you rest inside of, rather than something that unsettles you. Because if even mathematics, the most rigorous, certain discipline human beings have ever developed, contains truths beyond its own reach, then perhaps it is not so strange that you, too, carry questions you cannot answer. Perhaps that is not a failure of mind. Perhaps it is simply the shape of things. Chapter 3. The Prime Number Mystery. Chaos hiding inside order. Imagine you are walking along a very long road. The road stretches out ahead of you for as far as you can see, and beyond that, further still, infinitely further. In fact, because this road has no end. Along the road, there are lampposts. Some of them are clustered close together, almost touching, casting overlapping pools of light. Others stand alone, separated from their nearest neighbours by long, dark stretches of empty road. And as you walk further and further from where you started, the lampposts become rarer, the gaps between them grow longer, the darkness between them deepens. But no matter how far you walk, no matter how long the road becomes, the lampposts never stop appearing entirely. There is always, eventually, another one, waiting in the distance, solitary, irreducible, lit. Those lampposts are the prime numbers. A prime number is a whole number greater than one that can only be divided evenly by two things itself, and 1, 2 is prime, 3 is prime, 5, 7, 11, 13. They cannot be broken down into smaller factors. They are, in a very real sense, the atoms of arithmetic, the indivisible building blocks from which every other whole number is constructed. Take any number you like, say 60, you can break it down into smaller pieces. 60 is 2 times 30, 30 is 2 times 15, 15 is 3 times 5, and there you stop, because 2, 3, and 5 are all prime. Every whole number, no matter how large, can be expressed as a unique product of prime numbers. This is called the fundamental theorem of arithmetic. and it has been known since ancient Greece. And yet, for all their foundational importance, for all the centuries of scrutiny they have received, the prime numbers keep a secret that no mathematician has ever fully unlocked. Their distribution, the pattern of where they appear along that infinite road, remains one of the deepest, most stubbornly resistant mysteries in all of human knowledge. At first glance, the primes seem almost random. Look at the early ones: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. There is no simple formula that generates them. There is no obvious rhythm or cycle. You cannot look at a prime and reliably predict where the next one will be as numbers grow larger. The average gap between consecutive primes grows larger too, slowly, logarithmically, but within that general trend. The gaps themselves are wildly irregular. Sometimes two primes sit right next to each other, separated by only a single even number. These are called twin primes, and examples include 3 and 5, 11 and 13, 17 and 19. Whether twin primes continue appearing infinitely far along the number line is another question that remains, to this day, unanswered. We strongly suspect they do. We cannot prove it. And yet, and here is where the mystery deepens into something genuinely eerie, the primes are not truly random. Beneath their apparently chaotic surface, there is structure. There is order. There are patterns so deep and so precise that they have consumed the lives of some of the greatest mathematical minds in history. The primes only appear random when viewed from the surface. Look deeper, and you begin to sense something else entirely, something. The person who looked deepest and saw the most was a German mathematician named Bernhard Riemann. In 1859, Riemann published a short paper, only 8 pages long. That is widely considered the most important unpublished conjecture in the history of mathematics. I say unpublished conjecture because, remarkably, Riemann did not prove his central claim. He stated it, explored its consequences, and moved on. And in the century and a half since, no one has been able to prove it either. The claim he left behind, now known simply as the Riemann hypothesis, remains unproven to this day, carrying with it a $1 million prize from the Clay Mathematics Institute for whoever finally cracks it. So, what did Riemann see to understand it? We need to take a short, gentle detour into a mathematical object called the Riemann zeta function. Do not be put off by the name. The idea behind it is, at its core, a question about sums. You take a series of numbers, raise them to a certain power, and add them all together. Riemann extended this idea into the realm of complex numbers, numbers that have both a real part and an imaginary part, and in doing so, he created a function of extraordinary richness and depth. This function, when plotted in the complex plane, produces a landscape of peaks and valleys, of spiraling curves and converging sequences, and within that landscape, there are special points called zeros, places where the function equals nothing, where it touches the ground. Riemann noticed something remarkable about these zeros. The ones that seem to matter most, the ones he called the non-trivial zeros, all appeared to lie on a single vertical line in the complex plane, not scattered across the landscape, not distributed randomly, all of them, every single one he could calculate, sitting precisely on what mathematicians now call the critical line. And Riemann conjectured that this was not a coincidence, that all non-trivial zeros of the zeta function lie on this line always, without exception. Why does this matter for the prime numbers? Because Riemann discovered a profound and beautiful connection between the zeros of the zeta function and the distribution of the primes. The zeros are not merely abstract features of a complex function. They are, in a precise mathematical sense, the hidden frequencies that control where the primes appear. Think of it like this. Imagine the distribution of primes as a complex musical chord, a sound made up of many overlapping waves. Riemann found that the zeros of the zeta function are the individual notes of that chord. Each zero contributes a wave, and the waves combine to produce the pattern of the primes. The primes are not random noise. They are the output of a hidden symphony, and Riemann found the score. He just could not prove that every note was where he thought it was. In the decades since, mathematicians have calculated trillions of non-trivial zeros. Every single one sits precisely on the critical line. Not one exception has ever been found, and yet the hypothesis remains unproven. We have overwhelming computational evidence, but in mathematics, evidence is not proof. A pattern that holds for a trillion cases can still fail on the trillion and first. Mathematical truth requires certainty, not probability, and certainty here has not yet arrived. Pause here for a moment. Feel the strangeness of that. We have a pattern that has held without a single exception across trillions of verified cases, that underpins our deepest understanding of how the prime numbers are distributed, that connects two seemingly unrelated areas of mathematics through a bridge of breathtaking elegance, and we still do not know if it is true. We believe it. We feel it in the bones of the mathematics surrounding it, but we cannot prove it. And in mathematics, that gap between overwhelming conviction and absolute proof is an abyss. The practical stakes of all this are higher than most people realize. The security of the entire modern internet rests, in a very direct way, on the properties of prime numbers. When you enter your credit card details into a website, when you send a private message, when your bank confirms your identity across a digital network. The encryption protecting that transaction is built on the difficulty of factoring very large numbers back into their prime components. It is easy to multiply two large primes together and get an enormous number. It is extraordinarily difficult, given only that enormous number, to figure out which two primes were multiplied to produce it. That asymmetry, easy in one direction, hard in the other, is the lock on every digital door in the world. And that lock depends on properties of primes that we understand only partially, through a glass, darkly, with a hypothesis at the center of it all that remains, after 165 years, unproven. We are trusting our entire digital civilization to a pattern we do not fully understand. That is not an exaggeration. That is simply the state of affairs. And there is one more thing about the prime numbers that deserves a quiet moment of reflection before we move on. Something discovered relatively recently that struck the mathematical community with something close to wonder in 2012. The mathematician Tadashi Tokieda observed, and others later formalized, that prime numbers, when arranged in a spiral pattern known as the Ulam spiral, first doodled by the mathematician Stanislaw Ulam during a boring conference in 1963, revealed diagonal lines, visible, unmistakable diagonal lines running through what the primes are ancient. They existed before human beings gave them a name. They will exist long after the civilization that studies them has gone, and somewhere along that infinite road, in the long, dark stretches between the lamp posts. The answer to Riemann's question is waiting, patient, certain, true. We just haven't found it yet. Take a long, slow breath. Let the mystery of the primes settle around you like the dark between stars. They are out there, scattered along the number line, each one indivisible, each one alone, each one part of a pattern so deep that the greatest minds in history have devoted their lives to it without reaching the end. The primes hide order within apparent randomness. But some mathematical patterns go even further than that. Some patterns do not merely hide order. They contain entire worlds within themselves, infinite complexity, folded into a finite space, visible to anyone who knows how to look. We call them fractals. And where the primes feel ancient and austere, the world of fractals feels almost alive. That is where we are heading next, into shapes that contain infinity, into the mathematics of the endlessly repeating, the endlessly detailed, the endlessly strange. Rest for a moment, and then, gently, follow me in. Chapter 4. Fractals, Infinite Complexity in a Finite Space. There is a question that sounds, at first, almost childishly simple. How long is the coastline of Britain? You might think the answer is just a matter of looking it up, consulting a map, reading a number, moving on. But in 1967, a mathematician named Benoit Mandelbrot published a paper with that very question as its title, and his answer was not a number. His answer was, in essence, that the question itself was broken, that the coastline of Britain does not have a length, not because no one has measured it carefully enough, but because the more carefully you measure it, the longer it gets, and if you could measure it with infinite precision, it would be infinitely long. This is not a paradox born of imprecision or ignorance. It is a paradox born of the nature of coastlines themselves, and understanding why it is true opens a door into one of the most beautiful, most strange, and most quietly unsettling territories in all of mathematics. The territory of fractals. Here is the core of the coastline paradox. Imagine you are measuring the coast of Britain with a ruler 100 kilometers long. You place the ruler along the coast, stepping it around the bays and headlands in large, sweeping strides, and you arrive at a total length. Now imagine you replace that ruler with one 10 kilometers long. Now you can follow the coast more closely. You can trace around smaller bays, smaller peninsulas, smaller inlets that your larger ruler simply stepped over. Your total measurement is now longer than before. Replace the ruler with 1 kilometer and the measurement grows longer still. Follow every boulder, every rock, every grain of sand at the waterline, and the coastline keeps growing. There is no scale at which the coast becomes smooth. There is no resolution at which the detail runs out. The closer you look, the more there is to see. This property, the property of having detail at every scale, of never becoming simple no matter how closely you examine it, is the defining characteristic of a fractal. And once Mandelbrot had named it and begun to study, he found fractals everywhere, not just in coastlines, but in mountain ranges, in clouds, in the branching of rivers, in the structure of snowflakes, in the way trees divide into branches that divide into smaller branches that divide into still smaller ones. Each branching pattern a rough echo of the one above it. Nature, it turns out, is saturated with fractal geometry, and this raises a question that is, the longer you sit with it, increasingly difficult to dismiss. Why? Before we try to answer that, let us spend a moment with the most famous fractal of all, the the one that made fractals visible to the world, and that revealed just how much complexity can be generated by the simplest possible rules, the Mandelbrot set. The Mandelbrot set is generated by a single equation, an equation so simple that a child could write it down. Take a number, square it, and add the original number. Take the result, square it, and add the original number again. Repeat this process over and over, forever, for every possible starting number in the complex plane, some starting numbers. When you repeat this process, will produce values that shoot off toward infinity. Others will stay bounded, cycling within a finite range no matter how many times you repeat the operation. The Mandelbrot set is simply the collection of all starting numbers for which the values stay bounded. That is all it is, a sorting exercise, a boundary between numbers that run away and numbers that stay. And yet the shape of that boundary is one of the most astonishing objects in all of human intellectual history. When you plot the Mandelbrot set on a screen, coloring the bounded numbers black and coloring the escaping numbers according to how quickly they escape, what emerges is a shape of almost incomprehensible complexity and beauty. A large cardioid shape with a circular bulb attached, sprouting smaller bulbs, each of which sprouts still smaller ones, fringed at every scale with intricate tendrils and filaments, spiraling seahorse tails and elaborate antenna structures, each one containing, embedded within it, tiny perfect copies of the entire Mandelbrot set, not approximate copies, not rough echoes, exact, perfect, infinitely detailed copies, smaller than a pixel, smaller than a mathematical point, going on forever at every level of magnification. And all of this, every tendril, every spiral, every embedded copy of the whole, emerges from one equation, repeated, nothing more. Take a moment to let that breathe. A single rule, applied again and again, generates infinite complexity. The equation does not know it is producing beauty. It does not know it is producing anything. It is simply doing what it does, step after step. And the structure that emerges from that repetition is richer, stranger, and more detailed than anything a human being could consciously design. This is one of the most quietly profound things mathematics has ever revealed. That complexity does not require a complex cause. That simplicity, iterated, can produce worlds. Now, the Mandelbrot set is a purely mathematical object. It exists in the abstract realm of complex numbers, not in physical space. But here is where the story takes its unsettling turn. The same property, simple rules generating fractal complexity, appears to be operating throughout the physical world in systems that have no knowledge of mathematics, no awareness of rules, no designer of any kind. Consider a tree. A tree grows according to simple biological rules, grow upward and outward, branch when conditions allow. Repeat the branching pattern at smaller and smaller scales. The result is a fractal structure, a canopy that maximizes exposure to sunlight by distributing branches in a self-similar pattern across multiple scales. No architect designed this. No engineer optimized it. The tree arrived at fractal geometry because fractal geometry is, in a very deep sense, the most efficient solution to the problem of filling space with branches. Evolution did not invent fractals, it converged on them, because they were already the answer. The same convergence appears in the human body. Your lungs are fractal. The bronchial tubes branch and branch and branch again. each generation of branching creating smaller tubes in a self-similar pattern, until the surface area available for gas exchange reaches a staggering 20 to 25 times the surface area of your entire skin, all folded into a space roughly the size of 2 fists. Your circulatory system is fractal, branching from the aorta down through arteries and arterioles and capillaries in a self-similar cascade. The neurons in your brain form fractal networks. The surface of your cerebral cortex is folded in fractal patterns to maximize the area of neural tissue that can fit within the skull. You are, in a very literal sense, a fractal organism. Your body solved the problem of packing enormous functional surface area into a compact volume by using the same strategy that coastlines use, that trees use, that river deltas use, that snowflakes use, the strategy that emerges naturally whenever a system is governed by simple, self-repeating rules and has space to fill. And then there is the snowflake, perhaps the most familiar fractal in nature, and in some ways the most philosophically striking. Every snowflake begins as a single water molecule attaching to a tiny particle of dust as more water molecules attach. They do so according to the simple rules of molecular bonding, rules that produce a hexagonal symmetry. As the crystal grows, each of its 6 arms extends into the cold air, branching and subdividing in response to the temperature and humidity it encounters. Each arm experiences the same conditions, so each arm branches in the same way. The result is a structure of 6-fold symmetry, with branching patterns that repeat at smaller and smaller scales, each arm a fractal echo of the whole. No 2 snowflakes are identical, because no 2 take exactly the same path through the atmosphere. But every snowflake is fractal, because every snowflake grows by the same simple rules in a space that rewards self-similar branching. Now here is the question that fractal geometry quietly insists upon. If the same geometric strategy, fractal self-similarity across scales, appears independently in coastlines, trees, Mandelbrot called this the geometry of nature. He spent decades arguing against considerable resistance from the mathematical establishment that the classical geometry of smooth curves and perfect spheres was not the geometry of the world we actually live in. Clouds are not spheres, mountains are not cones, coastlines are not circles. The geometry of the real world is rough, self-similar, endlessly detailed. It is fractal. And now, decades after Mandelbrot's work, that argument has been so thoroughly vindicated that fractal geometry is a foundational tool in fields ranging from ecology to cardiology to computer graphics to the modeling of financial markets. There is one more property of fractals that deserves a quiet moment before we move on, a property that is, mathematically speaking, one of the strangest things in all of geometry. It is the concept of fractal dimension. In ordinary geometry, we are comfortable with whole number dimensions. A line is one-dimensional. A flat surface is two-dimensional. A solid object is three-dimensional. But fractals occupy a dimension that is not a whole number. The coastline of Britain has a fractal dimension of approximately 1.25. Somewhere between a line and a surface. The boundary of the Mandelbrot set has a fractal dimension of exactly 2, as complex, in a precise mathematical sense, as a filled plane, even though it is merely a boundary curve. Some natural fractals have dimensions of 1.7, 1.4, 2.3. They exist, mathematically speaking, in the spaces between the dimensions we are used to. They are more than a line, but perhaps that is the most unsettling thing about fractals. Not their beauty, extraordinary as it is, not their ubiquity in nature, remarkable as that is, but the fact that they reveal dimension itself to be a more complicated, more flexible, more mysterious concept than we ever imagined. That between the familiar whole numbers of our geometric world, there is room, infinite room, for structures of extraordinary strangeness, and nature fills that room eagerly, effortlessly, without being asked. Breathe slowly. Let the image of infinite detail settle around you. A snowflake outside a winter window, its arms branching and branching into the cold. A tree against a pale sky, its canopy a recursive echo of its roots. The coast of an island, unmeasurable, endlessly complex, folding in on itself at every scale, all of them speaking the same quiet mathematical language, all of them fractal, all of them, in their own way, infinite. Fractals show us that infinity can be folded into something you can hold in your hands. But infinity itself, as a concept, as a mathematical object in its own right, is far stranger than anything fractals can prepare you for, because it turns out that infinity is not one thing. It is not a single destination at the end of a very long road. Infinity comes in different sizes, and some infinities are, in a precise and proven mathematical sense, larger than others. That is the door we are walking through next, into the work of a man whose ideas were so radical, so unsettling to the mathematical establishment of his time, that his own colleagues tried to destroy his career. A man who stared into the infinite and came back changed. His name was Georg Cantor, and what he found there will stay with you. Rest for just a moment. And then, when you are ready, follow me. Chapter 5, Cantor's Infinities. Some infinities are larger than others. There is a hotel with infinitely many rooms. Every single room is occupied. A new guest arrives at the front desk and asks for a room, and the hotel accommodates them, not by finding a vacancy, not by turning anyone away, but by asking every existing guest to move one room down. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. And so on, forever, down the infinite corridor. Room 1 is now empty. The new guest checks in. The hotel is still full. This is Hilbert's Hotel, a thought experiment devised by the mathematician David Hilbert to illustrate just how strange and counterintuitive the mathematics of infinity really is. And it is only the beginning, because if you press a little further, the strangeness deepens considerably. What if infinitely many new guests arrive at once? The hotel can accommodate them too, by asking every existing guest to move to the room whose number is double their current room number. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. Every existing guest now occupies an even-numbered room, leaving all the odd-numbered rooms, infinitely many of them, empty and available for the new arrivals. A hotel that was completely full has, by a simple rearrangement, made room for infinitely many more guests without losing a single one. If that feels wrong to you, if something in your mind is quietly insisting that this cannot be right, that a full hotel cannot make room for more guests, that infinity plus infinity should be larger than infinity, then you are in excellent company. That instinct is the intuition of finite creatures living in a finite world, and it is a perfectly reasonable instinct. It is also, when applied to infinity, completely unreliable. Infinity does not behave the way finite things behave. It does not follow the rules your experience has taught you. And the mathematician who first mapped its true territory with rigorous precision was Georg Cantor, a man whose ideas were so radical, so deeply threatening to the mathematical consensus of his time, that the establishment did not simply disagree with him, they tried to erase him. Georg Cantor was born in 1845 in St. Petersburg, Russia, and spent most of his mathematical career in Germany. He was, by all accounts, a deeply earnest and intellectually passionate man, driven by a genuine belief that the mathematics of the infinite was not merely an abstract curiosity, but a window into something profound and real. He corresponded with theologians as readily as with mathematicians, convinced that his work on infinity had implications for the nature of God and the structure of existence. His colleagues found this unsettling. His mentor, Leopold Kronecker, found it unforgivable. Kronecker, one of the most influential mathematicians of the era, called Cantor's work a corruption of mathematics, a disease infecting the discipline, and Cantor himself a corrupter of youth. He campaigned actively to block Cantor's career, to prevent his papers from being published, to discredit his ideas among the mathematical. What ideas were worth all of that resistance? What had Cantor seen that was so threatening? He had seen that infinity is not one thing. He had proven with rigorous mathematical logic that there are different sizes of infinity, that some infinite collections are, in a precise and meaningful sense, strictly larger than others. And to understand why this is true and why it is so deeply strange, we need to think carefully about what it means for two collections to be the same size. In ordinary life, we compare the sizes of collections by counting them. You have 5 apples and I have 5 oranges, so we have the same number of fruit. But what if the collections are too large to count? What if they are infinite? Cantor's insight was to use a different method entirely, one that does not require counting at all. 2 collections of the same size, Cantor proposed, if and only if you can pair up their members in a perfect one-to-one correspondence. Every member of the first collection paired with exactly one member of the second, every member of the second paired with exactly one member of the first, with nothing left over on either side. This seems obvious for finite collections. 5 apples pair perfectly with 5 oranges, so they are the same size. But when you apply this criterion to infinite collections, something extraordinary happens. Consider the counting numbers 1, 2, 3, 4, 5 going on forever, and consider the even numbers 2, 4, 6, 8, 10 going on forever. Your instinct might say that there are fewer even numbers than counting numbers because the even numbers are only every other one. But watch what happens when you try to pair them up. Pair 1 with 2, 2 with 4, 3 with 6, 4 with 8, 5 with 10. Every counting number pairs perfectly with exactly one even number. Just double it. Every even number pairs perfectly with exactly one counting number. Just halve it. The pairing is perfect. Nothing is left over. By Cantor's criterion, the counting numbers and the even numbers are exactly the same size. There are just as many even numbers as there are counting numbers, even though the even numbers are a subset of the counting numbers. In the infinite, a part can be the same size as the whole. This is not a trick. This is not a semantic game. This is a precise mathematical fact. Cantor called collections that can be paired with the counting numbers countably infinite. and he denoted the size of this infinity with the symbol 0, Aleph Null, the first letter of the Hebrew alphabet, with a subscript 0. The counting numbers are Aleph Null. The even numbers are Aleph Null. The odd numbers are Aleph Null. The integers, all positive and negative whole numbers together, are Aleph Null. The rational numbers, all fractions, all ratios of whole numbers are, perhaps surprisingly, also Aleph Null. Cantor proved this with an elegant zigzag argument, showing how to arrange all fractions in a grid and then trace a path through them that visits every single. And then Cantor turned his attention to the real numbers, the numbers that include not just whole numbers and fractions, but all the irrational numbers too, the square roots, the transcendental numbers like pi and e, the numbers whose decimal expansions go on forever without repeating, the real numbers between 0 and 1 alone. And what he found there cracked the mathematics of infinity wide open. He proved, and the proof is so elegant, so precise, so devastating in its simplicity, that the real numbers between 0 and 1 cannot be paired with the counting numbers. No matter how clever your pairing scheme, no matter how carefully you try to list all the real numbers between 0 and 1, your list will always necessarily be incomplete. There will always be real numbers that your list misses, not because you ran out of time or made an error, but because the real numbers between 0 and 1 are, in a fundamental mathematical sense, too numerous to be listed. Their infinity is of a strictly larger kind than the infinity of the counting numbers. The proof Cantor used is called the diagonal argument, and it is one of the most beautiful pieces of mathematical reasoning ever devised. Suppose, for the sake of argument, that someone hands you a list, an infinite list, that they claim contains every real number between 0 and 1. Each number on the list is a decimal expansion, 0 point something going on forever. The first number on the list has some digit in its first decimal place. The second number has some digit in its second decimal place. The third number has some digit in its third decimal place, and so on. Now Cantor says, look at the diagonal. Look at the first decimal digit of the first number, the second decimal digit of the second number, the third decimal digit of the third number, and so on down the diagonal of the list. Take each of those digits and change it. If it is a 3, make it a 4. If it is a 7, make it an 8. Change every digit to something different. Now assemble those changed digits into a new number. This new number differs from the first number on the list in its first decimal place. It differs from the second number in its second decimal place. It differs from the third number in its third decimal place. It differs from every number on the list in at least one decimal place. Therefore, it is not on the list. But it is a real number between 0 and 1. Therefore, the list was incomplete, and this argument works for any list you could ever construct. There is no way to list all the real numbers. Their infinity is uncountable. Pause here. Breathe. The infinity of the real numbers is strictly larger than the infinity of the counting numbers. Not larger in some vague metaphorical sense. Larger in a precise, proven, mathematical sense. There is a hierarchy of infinities. Each between Aleph Null and Aleph 1, Cantor posed what he called the continuum hypothesis, the question of whether there is any size of infinity between the countable and the uncountable, or whether they are adjacent levels with nothing in between. This question tormented him. He spent years trying to prove it, ultimately convinced he had succeeded, and devastated when his proofs collapsed. and in one of the most extraordinary outcomes in the history of mathematics, it was eventually shown by Kurt Gödel in 1940 and Paul Cohen in 1963 that the continuum hypothesis is independent of the standard axioms of mathematics. It can neither be proven nor disproven within the standard system. It is, in the most precise sense possible, a Gödelian truth, a question that mathematics can formulate but cannot answer from within itself. Cantor did not live to see this resolution, but in a strange way it vindicates everything he believed, that infinity was not a simple monolithic thing, but a vast and layered territory with depths that exceeded the reach of any single mathematical system. There is something deeply human in Cantor's story, a man who saw further than his contemporaries, who was punished for it, who struggled under the weight of ideas too large for the world he lived in, who spent his final years in a sanatorium named for the saint of the impossible, and who was, in the end, right, completely, profoundly, unambiguously right. The real numbers between 0 and 1 contain more points than there are counting numbers in all of existence. Let that sit in the quiet for a moment. In the space between 0 and 1, a gap you could cover with your finger on a number line, there is a greater infinity than the infinity of all the whole numbers, stretching endlessly in both directions. Infinity is not a destination, it is a landscape, and some parts of that landscape are larger than others. Rest in that for a moment. Let the hierarchy of infinities dissolve into the background of your breathing. Small, then smaller still, until the numbers blur and the quiet takes over. Because we are about to leave the realm of the infinitely large and step into something that will unsettle you in an entirely different way. We are about to encounter a sum, a simple, seemingly childish sum, 1 plus 2 plus 3 plus 4, going on forever, and we are going to arrive at an answer that should be impossible, an answer that is, in a very real sense, wrong. And yet an answer that the universe insists upon again and again in the equations that describe the most fundamental structure of physical reality. The answer is -1/12, and by the time we are done, you will understand why that is simultaneously absurd, beautiful, and deeply, quietly disturbing. Follow me. Chapter 6. The Sum That Should Not Exist. Let us begin with something simple, something so simple that a child in their first years of school could understand it. We are going to add up numbers, whole numbers, positive numbers, the most innocent, unambiguous kind of numbers there are. We will start with 1, and then add 2, and then add 3, and then add 4, and we will keep going forever, adding every positive whole number to the sum, one after another, without stopping. What do you get? Your instinct, and it is a perfectly reasonable instinct, the instinct of a clear and logical mind, is that the sum grows without bound, that it climbs and climbs and climbs, racing toward infinity, never settling, never converging, never arriving anywhere finite. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. The partial sums are accelerating. There is no ceiling. The answer, clearly and obviously, is infinity. And in the most straightforward mathematical sense, you are correct. The sum of all positive integers, interpreted in the ordinary way, diverges. It does not converge to a finite value. Any first course in calculus will tell you this. Any mathematician will confirm it. The sum is infinite. Case closed. Except that it is not closed, because the universe, it turns out, has not read the introductory calculus textbook. and in the places where mathematics touches the deepest structure of physical reality, in the quantum field theories that describe the behavior of subatomic particles, in the string theory that attempts to unify all of physics, in the laboratory measurements of forces between metal plates separated by a vacuum, the sum of all positive integers appears, and where it appears, the value it takes is not infinity. It is negative 1/12. This result is so counterintuitive, so apparently absurd, so violently at odds with common sense, that when people encounter it for the first time, they often assume it is a joke, a mathematical prank, a sleight of hand designed to confuse. It is none of those things. It is one of the most rigorously verified, most practically consequential, most deeply strange results in all of mathematics, and understanding why it is true, or rather, in what precise sense it is true, requires us to expand our idea of what mathematics is actually doing when it assigns a value to a sum. Let us begin with a simpler example. Consider the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1, going on forever. This is called Grandi's series, after the Italian mathematician Guido Grandi, who studied it in the early 18th century. What does it equal? If you stop after an odd number of terms, the partial sum is 1. If you stop after an even number of terms, the partial sum is 0. The series oscillates between 1 and 0 forever, never settling. In the ordinary sense, it does not converge. It has no sum. But there is another way to think about it. If the sum has any consistent value at all, call it S, then notice that 1 minus S is 1 minus the whole series, which is 1 minus 1 plus 1 minus 1 plus 1, which is just S, again written from the second term onward. So 1 minus S equals S, which gives 2S equals 1, which gives S equals 1/2. The value 1/2 is not where the series lands. It never lands anywhere, but it is, in a precise sense, the average of its oscillations, the center of gravity of its behavior. This is not ordinary summation. It is a different, more subtle operation, one that extracts a meaningful, finite value from a series that does not converge in the conventional sense. Mathematicians call this process regularization, and there are several rigorous methods for doing it. They go by names like Cesaro summation, Abel summation, Ramanujan summation, and analytic continuation. Each method is precisely defined, internally consistent, and applicable to specific classes of series. They are not guesswork. They are not tricks. They are legitimate mathematical operations, as rigorous as ordinary addition, operating on a different level of abstraction. And when you apply the most powerful of these methods to the sum of all positive integers, you get negative 1/12 every time, consistently, without exception. The method most directly responsible for this result is called analytic continuation, and it works through an object we encountered briefly in our conversation about prime numbers, the Riemann zeta function. Recall that the zeta function takes a number s and produces a sum, 1 to the power of negative s plus 2 to the power of negative s plus 3 to the power of negative s, and so on, when s is greater than 1. This sum converges to a finite value, when s equals 2. For example, the sum converges to pi squared divided by 6, another appearance of pi in a place it has no obvious right to be. When s equals 1, the sum diverges. It is the famous harmonic series, which grows without bound. When s is 0 or negative, The sum as written diverges. But here is the remarkable thing about the zeta function. Even though the sum diverges for values of s at 0 and below, the function itself, the deeper mathematical object that the sum approximates for large S, can be extended through a process called analytic continuation to cover those values too. The extended function is smooth, well-defined, and unique. There is only one way to extend it consistently, and when you evaluate the extended zeta function at s equals -1, which corresponds to the sum 1 plus 2 plus 3 plus 4 going on forever, the value you get is -1/12. This is not a coincidence. It is not an approximation. It is the exact, precise, unavoidable value that the mathematics produces when you ask it, in the most sophisticated way available, what the sum of all positive integers means. Pause here for a moment. Let the strangeness of this settle. Now let us talk about the man who saw this most clearly, and who arrived at results like this not through years of graduate training, but through something that even today mathematicians struggle to fully explain. Srinivasa Ramanujan was born in 1887 in a small town in southern India. He grew up in poverty, educated himself in mathematics almost entirely through a single outdated textbook, and filled notebook after notebook with results. Thousands of formulas, identities, and theorems that he claimed came to him in dreams. His family goddess, Namagiri, he said, would write equations on his tongue while he slept, and he would wake and record them before they faded. Whether you interpret this in 1913, Ramanujan wrote a letter to G.H. Hardy, a prominent mathematician at Cambridge University, enclosing pages of his results with no proofs, no explanations, no context. Hardy's first reaction was skepticism bordering on dismissal. The results looked either like the work of a crank or the work of a genius, and he could not immediately tell which. He showed the letter to his colleague, J.E. Littlewood, and together they spent an evening working through the formulas. By the end of the evening, they had concluded that only a mathematician of the highest order could have produced them. Hardy later said it was one of the most extraordinary mathematical letters he had ever received in his life, and that many of the results had completely defeated him. He had no idea how Ramanujan had arrived at them, let alone whether they were correct. Ramanujan came to Cambridge. He and Hardy collaborated for years, producing mathematics of astonishing depth and originality. But Ramanujan was fragile. The English climate disagreed with him. The food disagreed with him. He was a strict vegetarian, and wartime Cambridge offered little that suited his diet. He fell ill with tuberculosis, or possibly a different illness misdiagnosed as tuberculosis, and returned to India, where he died in 1920 at the age of 32. He left behind notebooks filled with thousands of results, many of which mathematicians are still working to fully understand and verify more than a century later. Some of his formulas, when finally proven, required mathematical machinery that did not exist in Ramanujan's time and that he could not possibly have known about. How he knew the results were true. The result we are discussing tonight, the assignment of -1/12 to the sum of all positive integers, appears in Ramanujan's notebooks in his own hand. He did not call it a trick or an approximation. He wrote it as a straightforward fact, and in the decades since, its appearance in physics has vindicated his confidence in a way that still feels slightly miraculous. The most striking physical appearance of this result is in a phenomenon called the Casimir effect. In 1948, the Dutch physicist Hendrik Casimir predicted that two uncharged, perfectly conducting metal plates, placed very close together in a vacuum, would experience a small but measurable attractive force. The prediction seemed bizarre. There is nothing between the plates, no matter, no charge, no field in the classical sense. What could possibly be pushing them together? The answer lies in quantum field theory, which tells us that even empty space is not truly empty. It is filled with quantum fluctuations, fleeting, ghostly oscillations of quantum fields that pop in and out of existence continuously. These fluctuations have energy and the plates, by imposing a boundary on the space between them, restrict which fluctuations can exist in that space. Only fluctuations whose wavelengths fit neatly between the plates are permitted. Outside the plates, all fluctuations are permitted. The result is a difference in energy density between inside and outside, which produces a net force pushing the plates together. And the mathematical calculation of this force involves, at its heart, the sum over all the permitted modes of the sum of all positive integers, assigned the value -1/12 through the rigorous process of analytic continuation, produces a physically correct prediction of a measurable force in a laboratory. This is not mathematics playing games. This is mathematics telling us something true about the structure of reality, something so deep and so strange that our ordinary intuitions about addition simply cannot reach it. What does this mean? It means that the mathematics we use every day, the arithmetic of the counting numbers, the addition we learned as children, is not the whole story. It is a special case, a low-resolution version of a much richer, much stranger mathematical reality. When we say that 1 + 2 + 3 goes to infinity, we are applying ordinary arithmetic to a question that ordinary arithmetic is not equipped to answer when we apply the more powerful tools of analytic continuation. We access a deeper layer of mathematical truth, one that is consistent, rigorous, and apparently built into the structure of the physical universe. Breathe slowly. Let the impossibility of it settle into something softer, something like wonder. There is a version of mathematics that your intuition can reach, and there is a deeper version that it cannot. The deeper version is not wrong. It is not a trick. It is simply operating at a level of abstraction where the rules are different, where sums that diverge in the shallow water converge in the deep, where a number as strange and negative and fractional as -1/12 turns out to be exactly right. Ramanujan saw this. The universe knows this. And now, quietly, in the late hours of this long night, so do you. He saw mathematics in his dreams, arriving as visions, as gifts from something beyond the ordinary reach of conscious reasoning. And in a way, everything we have been exploring tonight has that quality. The quality of a truth that seems to come from somewhere deeper than the place where we usually look. The golden ratio is another such truth, a number that no one planted in the world, and yet the world keeps writing it everywhere it grows. That is where we go next, into 5, into the number that nature cannot stop using, into the ratio that turns up in the spiral of a shell, the seed head of a sunflower, the branching of your own veins, quiet, persistent, and entirely unexplained, Rest for a moment, and then follow me. Chapter 7. The Golden Ratio, a number that should not be everywhere. There is a number that the universe seems to prefer. Not loudly, not obviously, not in a way that announces itself or demands attention, but quietly, persistently, in the way that a particular shade of light keeps appearing in different rooms of the same house. You notice it once, and then you cannot stop noticing it. It turns up in the spiral of a nautilus shell and the arrangement of seeds in a sunflower. It appears in the proportions of the human body and the branching angles of trees. It emerges from one of the simplest sequences in all of mathematics, and it sits at the heart of some of the most beautiful geometric constructions ever devised. It has been called the divine proportion, the golden section, the mean of means. Mathematicians call it phi, and its approximate value is 1.618. That number, 1.618, is the golden ratio, and the longer you spend with it, the stranger it becomes. Let us begin with the simplest possible definition. Take a line segment and divide it into two pieces, a longer piece and a shorter piece, in such a way that the ratio of the whole line to the longer piece is exactly equal to the ratio of the longer piece to the shorter piece, that is all. A simple proportional relationship between three lengths. And the ratio that satisfies this condition, the one number that makes the proportion work out perfectly, is phi. 1.618, going on forever without repeating, an irrational number like pi, a number that cannot be expressed as a fraction of two whole numbers, a number that exists in the space between the rational and the whole. This geometric definition is ancient. The Greeks knew it. Euclid described it in his Elements, the foundational text of geometry written around 300 BCE. But it was in the Renaissance that phi acquired its mystical reputation. When the mathematician Luca Pacioli wrote a book in 1509 called De Divina Proportione, on the divine proportion, illustrated by Leonardo da Vinci, in which he argued that the golden ratio possessed properties so extraordinary, so harmonious, so reflective of divine order, that it deserved to be considered sacred. Leonardo's illustrations for the book include the famous Vitruvian Man, the drawing of a human figure inscribed in a circle and a square, and the proportions of the human body depicted there are, Pacioli argued, governed throughout by phi. The claim that the golden ratio is consciously embedded in great works of art and architecture, the Parthenon, the pyramids, the paintings of Leonardo, is, it should be said, a matter of considerable debate among historians and art scholars. Many of the supposed appearances of phi in famous artworks do not survive rigorous measurement. The human tendency to find meaningful patterns is powerful enough to discover phi almost anywhere if you are looking for it and are willing to measure loosely. We should hold those specific claims lightly, but here is what is not a matter of debate. Here is what is precise, measured, and mathematically verified. The golden ratio appears with stunning regularity in the living world, and its appearances there are not the result of human design or human preference. They are the result of growth. To understand how, we need to meet the Fibonacci sequence. The sequence was introduced to European mathematics by the Italian mathematician Leonardo of Pisa, known as Fibonacci, in his 1202 book Liber Abaci. The sequence itself is simplicity itself. You start with 1 and 1. Each subsequent number is the sum of the two numbers before it. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, and so on forever. There is nothing exotic about the rule. It is about as simple as a mathematical rule can be. And yet something extraordinary happens when you look at the ratios of consecutive Fibonacci numbers. Divide the second by the first. 1 divided by 1 is 1. Divide the third by the second. 2 divided by 1 is 2. Divide the fourth by the third. 3 divided by 2 is 1.5. Divide the fifth by the fourth. 5 divided by 3 is 1.666. Divide the sixth by the fifth. 8 divided by 5 is 1.6. Divide the seventh by the sixth. 13 divided by 8 is 1.625. The ratios are converging. They are approaching a limit, and that limit, with mathematical precision, is 5. The golden ratio emerges inevitably and exactly from the simplest possible additive sequence. It does not need to be put there. It arrives on its own. Now here is where the living world enters. Plants face a particular geometric challenge. They need to grow leaves, petals, seeds, and branches in arrangements that maximize their exposure to sunlight, their access to nutrients, their structural stability. And the solution that plant growth converges on, again and again across wildly different species, is to place each new element at an angle of approximately 137.5 degrees from the previous one. Turn by that angle, place a leaf or a seed, turn by that angle again, place the next one, and so on, spiraling outward as the plant grows. That angle, 137.5 degrees, is called the golden angle, and it is derived directly from phi. It is the angle you get when you divide a full circle in the ratio of the golden ratio. When a plant grows by rotating through the golden angle with each new element, something remarkable happens. The elements never line up perfectly into straight rows, because the golden angle, being based on an irrational number, never repeats exactly. The arrangement never becomes periodic. It never creates a straight spoke that blocks elements further from the center. Instead, it distributes elements with maximum efficiency, filling the available space as evenly and densely as possible, with no gaps, no clustering, no wasted room. And the spirals that emerge from this arrangement, the visible spiral patterns on a sunflower's seed head, on a pine cone, on a pineapple, on the scales of a pine cone, those spirals appear in pairs, always in adjacent Fibonacci numbers. A sunflower typically has 34 spirals running clockwise and 55 running counterclockwise, or 55 and 89, or 89 and 144 in the largest sunflowers. Always Fibonacci numbers, always adjacent ones, always therefore in a ratio approaching phi. This is not coincidence. This is not human projection. This is mathematics operating in biology with the precision of a physical law. The sunflower did not study Fibonacci. It did not calculate the golden angle. It simply grew according to a biochemical rule. Add each new element at a fixed angle from the previous one, and that rule, combined with the geometry of circular growth, produced Fibonacci spirals automatically. The mathematics was already there waiting in the geometry. The plant merely followed the path of least resistance, and the path of least resistance happened to run directly through one of the most famous numbers in all of mathematics. Pause here. Take a slow breath. The nautilus shell is another story worth dwelling on. The nautilus grows its shell by adding new chambers, each one a fixed proportion larger than the one before. The result is a spiral that maintains the same shape as it grows. Mathematicians call this an equiangular spiral or a logarithmic spiral, and the ratio governing its expansion is, in many nautilus specimens, very close to phi. Not all nautili produce precisely the golden ratio, the claim is sometimes overstated, but the logarithmic spiral itself, the shape that grows while remaining self-similar, is intimately connected to phi in a mathematical sense that goes deeper than any single measurement. It is the natural shape of growth that preserves proportion, and proportion, in the deepest sense, is what phi is about. The human body offers more examples, though again we should be careful about over-claiming. The ratio of the forearm to the hand, of the full arm to the forearm, of the height of the navel to the total height, these ratios cluster around phi in many individuals, though not with the mathematical precision of a sunflower's seeds. The skeleton, too, shows Fibonacci proportions in the arrangement of finger bones, 3 bones in each finger in lengths approximating Fibonacci ratios. These proportions are not perfectly golden, but they are closer to phi than chance would predict. And the reason, again, is likely to be the efficiency of growth. The same pressure toward optimal proportion that drives the sunflower toward Fibonacci spirals may drive the development of skeletal proportions toward Fi. Now step back even further. Look at the spiral galaxy. The Milky Way, like most spiral galaxies, has arms that follow logarithmic spirals, the same family of spirals that the Nautilus traces, the same spirals that emerge from the golden angle. The physical reasons are different from those that govern plant growth or shell formation. In galaxies, the spirals arise from density waves in the rotating disk of stars and gas. But the mathematical shape, the logarithmic spiral, the geometry of self-similar growth is the same. From the scale of a finger bone to the scale of a galaxy 100,000 light-years across, the same geometric family keeps appearing. The question this raises, the question that phi, for all its beauty, cannot answer, is why? Why does this number, defined by such a simple proportional relationship, turn out to be the solution to so many different optimization problems in so many different systems at so many different scales? Is it simply that phi is, in a mathematical sense, the most irrational number, the number that is hardest to approximate by simple fractions, and therefore the one that resists periodic clustering most effectively? That is part of the answer, and it is a real part. Phi's irrationality is not just poetic, it has specific mathematical properties that make it the optimal choice for spacing problems of a certain type. The sunflower is not choosing phi because it is beautiful, it is arriving at phi because phi is the solution. But something about that answer feels incomplete, because phi does not appear only in spacing problems. It appears in ratios, in proportions, in the convergence of the simplest possible additive sequence, in the geometry of pentagons and dodecahedra, in the continued fraction that is, of all possible continued fractions, the simplest, just ones, all the way down, forever. Phi is the limit of 1 plus 1 divided by 1 plus 1 divided by 1 plus 1 divided by 1, continuing forever. It is the most self-referential number in mathematics. It is equal to 1 plus 1 divided by itself. Its square is equal to itself plus 1. It is woven into the structure of mathematics at a level that seems almost too fundamental to be accidental. And perhaps that is the most honest thing to say about phi. Not that it is magical, not that the universe was designed around it, but that it sits at a kind of mathematical crossroads where simplicity, self-reference, and geometric efficiency all converge simultaneously. It is the number you keep arriving at when you follow the simplest possible rules as far as they will go. And because nature too tends to follow simple rules and follow them as far as they will go, Nature keeps arriving at phi, not by design, by inevitability. There is something deeply peaceful in that idea, if you let it settle, that the universe does not need a designer to produce beauty and proportion. That beauty and proportion are what you get when simple rules operate freely in space and time. That the golden ratio is not a secret message or a divine signature, but something almost more wonderful, the natural resting place of growth itself. Let your breathing slow. Imagine a single sunflower seed placed at the center of an empty disk, then another, each one rotated by the golden angle from the last, spiraling outward in a pattern that has never been designed and is never the same twice, and yet always produces the same spirals, always arrives at Fibonacci numbers, always converges to phi. Order without a designer, beauty without intention, pattern without a plan. The golden ratio is a number that the universe prefers not because anyone chose it, but because no one needs to choose what is already inevitable. And yet, for all the quiet beauty of phi, the universe also contains patterns of a very different character. Patterns that are not beautiful in any comfortable sense. Patterns that reveal not order hidden within apparent chaos, but chaos hidden within perfect order. Patterns that show us how a system can obey exact mathematical laws and yet remain, in principle, forever unpredictable. We call this chaos theory, and the man who discovered it was not looking for it at all. He was trying to predict the weather, and what he found instead changed our understanding of determinism, prediction, and the nature of the future itself. That is where we are going next, into chaos, into the mathematics of the butterfly and the storm, into the strange and humbling discovery that knowing the rules does not mean knowing the outcome. Rest for a moment, and then gently follow me. Chapter 8. Chaos Theory, the butterfly that broke prediction. In the winter of 1961, a meteorologist at the Massachusetts Institute of Technology made a small decision that changed the history of science. His name was Edward Lorenz, and he was running a weather simulation on one of the early room-sized computers of that era, a machine called the Royal McBee LGP-30, which hummed and clicked its way through numerical calculations at a pace that today's smartphones would find laughable. Lorenz had been running a simulation of atmospheric conditions, watching the computer trace out the behavior of temperature, pressure, and wind over simulated time. He wanted to examine a particular sequence more closely, so he did what seemed like the most natural and harmless thing in the world. He stopped the simulation, took the numbers the computer had printed out, the state of the system at a particular moment, and typed them back in as starting conditions. Then let the simulation run again from that point. He expected to see the same sequence continue. The computer was deterministic. It followed precise mathematical rules. The same inputs should produce the same outputs. He went for a coffee, came back, and found something that made no sense. The simulation had diverged completely. What had begun as an almost identical rerun of the same sequence had, over simulated weeks and months, evolved into something entirely different. The two runs shared the same starting conditions, or so it seemed. Lorenz looked more carefully and found the explanation. The computer's internal calculations used numbers with 6 decimal places of precision. But the printout instead, it had produced a completely different weather pattern. Lorenz sat with this discovery for a long time. He was a careful, methodical scientist. not given to dramatic conclusions. He checked his computer for errors. He checked his equations. He checked his inputs. Everything was correct. The divergence was not a mistake. It was a feature of the system itself. He had stumbled, almost by accident, onto one of the deepest and most consequential properties of certain mathematical systems, the property that would eventually become known as sensitive dependence on initial conditions, the property at the heart of what we now call chaos theory. Let us be precise about what chaos theory is and what it is not, because the word chaos carries connotations in ordinary language that are misleading in this context. A chaotic system, in the mathematical sense, is not a random system. It is not a disordered system. It is not a system without rules. A chaotic system is a deterministic system, one governed by exact, precise, well-defined mathematical equations, in which the long-term behavior is exquisitely sensitive to the precise values of the starting conditions. Change the starting conditions by any amount, however small, and over sufficiently long time. The trajectory of the system will diverge completely from what it would otherwise have been, not approximately, not partially, completely. The implications of this are profound, and if you sit with them long, quietly vertiginous, consider what it means for prediction. In classical physics, the physics of Newton and Laplace, the universe was imagined as a vast clockwork mechanism. Given perfect knowledge of the position and velocity of every particle in the universe at a single moment, a sufficiently powerful intelligence could calculate the entire future with perfect precision. This vision of a deterministic, predictable universe, sometimes called Laplace's demon, was the foundational assumption of scientific determinism for 2 centuries. The rules are known. The initial conditions, in principle, can be measured. Therefore, the future, in principle, can be predicted. Chaos theory does not overthrow this vision entirely. The rules are still known. The system is still deterministic, but it reveals a fatal practical limitation that no amount of improved measurement can ever overcome in a chaotic system. The precision required to predict the long-term behavior grows exponentially with the time horizon of the prediction. To predict the weather 1 day in advance requires knowing the initial conditions to a certain level of precision. To predict it 2 days in advance requires knowing them to a much higher level of precision. 3 days in advance requires still higher precision. The precision required doubles roughly every few days, which means that to predict the weather 2 weeks in advance would require knowing the initial state of the atmosphere to a precision so extraordinary that it would effectively require measuring every molecule of air in the entire atmosphere simultaneously, which is, in any practical sense, this is the original butterfly effect, a term that Lorentz himself eventually coined in a 1972 paper whose title asked whether the flap of a butterfly's wings in Brazil could set off a tornado in Texas. The answer, strictly speaking, is yes. Not that any particular butterfly causes any particular tornado, but that the atmosphere is sensitive enough to initial conditions that a disturbance as small as a butterfly's wing beat can, over sufficient time, shift the trajectory of the entire weather system into a completely different state. The butterfly does not create the tornado's energy. It merely nudges the initial conditions by an infinitesimal amount, and in a chaotic system, an infinitesimal nudge in the present can correspond to an enormous difference in the future. Pause here for a moment. Let that breathe, because this is where the mathematics becomes not just intellectually interesting, but almost philosophical in its weight. We live in a universe governed by deterministic laws. Everything that happens follows, in principle, from what came before. The laws of physics leave no room for gaps, no spaces where the future is undetermined by the past. And yet, because of chaos, the future is not predictable, not from any finite amount of information about the present, not to any useful degree of accuracy beyond a certain time horizon. Determinism and unpredictability coexist. They are not in tension. They are, in chaotic systems, the same thing seen from different angles. Lorenz went on to characterize the behavior of chaotic systems in greater depth, and in doing so produced one of the most iconic images in the history of mathematics. He simplified his atmospheric equations to a system of just 3 coupled differential equations, equations that describe how 3 variables change in relation to each other over time. This simplified system is called the Lorenz system, and when you plot the trajectory of its variables in 3-dimensional space, trace out the path that the system follows as it evolves through time, the result is a shape of extraordinary and haunting beauty. The trajectory spirals outward around one region of space, then flips and spirals around another region, then flips back, and continues like this forever, never repeating, never crossing itself, never settling into a fixed point or a simple cycle, and yet never flying off to infinity. It stays within a bounded region of space, tracing an endlessly complex, endlessly non-repeating path that resembles, from a distance, the wings of a butterfly. This shape, this strange, bounded, non-repeating trajectory is called the Lorenz attractor, and it is one of the first examples of what mathematicians call a strange attractor, a geometric object that captures the long-term behavior of a chaotic system. The Lorenz attractor is strange in a precise mathematical sense. It is a fractal. Its dimension is not a whole number. It is approximately 2.06, sitting just barely above a surface in 3-dimensional space. It is the footprint of chaos, written in geometry. And it is beautiful in the way that only things that are simultaneously ordered and inexhaustible can be beautiful. You can follow its path forever and never see the same point twice. You can zoom in at any scale and find the same intricate structure. It is, in the most literal sense, a portrait of bounded infinity, infinite variety contained within a finite space. Now consider the double pendulum. It is one of the simplest physical systems that exhibits chaotic behavior, and it is worth imagining in some detail because it illustrates the strangeness of chaos with a directness that atmospheric equations cannot. Take a pendulum, a weight on a rod, swinging back and forth, perfectly predictable, classic Newtonian mechanics. Now attach a second pendulum to the end of the first, a second weight on a second rod, free to swing from the bottom of the first pendulum. This is the double pendulum. Its motion is governed entirely by classical physics. There is no randomness in its equations. Every moment of its motion follows exactly and precisely from the moment before, governed by Newton's laws of motion without exception or approximation. And yet, if you release 2 double pendulums from starting positions that differ by an amount too small for any instrument to detect, their subsequent motions will diverge completely within seconds. One might swing in large, looping arcs. The other might flip wildly in apparently random directions. They started together. They were governed by the same laws. They arrive at completely different places. Watch a double pendulum swing, and you are watching determinism and unpredictability occupying the same body simultaneously. Order and chaos, not alternating but coexisting, woven together in the same equations. There is a deeper implication lurking here that deserves its own quiet moment. If the universe is governed by deterministic laws and quantum mechanics aside, the evidence is strong that it is, at the scales we experience directly. And if chaotic sensitivity is a widespread feature of physical systems, and it is, appearing in fluid dynamics, in the orbits of planets and asteroids, in the behavior of ecosystems, in the dynamics of the heart, in the firing patterns of neurons, then the future is, in a very practical sense, unknowable, not because it is not determined, but because the precision required to predict it exceeds anything that can be achieved, measured, or even in principle represented in a finite universe. The Laplacian dream of perfect prediction was never realistic, not because the universe lacks rules, but because the rules of the universe produce, in their operation, a complexity that outruns any finite description. The clockwork was always there, but the gears were always too fine to count. What does chaos theory say about free will? This is a question that philosophers have turned over carefully since Lorenz's discovery, and it does not have a clean answer. If the future is determined but unpredictable, then the question of whether our choices are free becomes genuinely complicated. Our decisions emerge from brain states that are themselves physical systems, electrochemical systems of enormous complexity, operating at scales where quantum effects may introduce genuine randomness, and at larger scales where chaotic sensitivity may amplify tiny fluctuations into macroscopic differences in behavior. Whether that constitutes freedom in any meaningful sense is a question mathematics can illuminate but not resolve. What chaos theory does tell us, clearly, rigorously, without ambiguity, is that the future is not written anywhere accessible. It is not stored in any book or computer or physical system that could be consulted. It will emerge moment by moment from initial conditions of such precision that they cannot be specified. In a system of such sensitivity that any deviation from those conditions would produce a different future, the future is real, it is determined, and it is, for all practical purposes, genuinely open. Rest in that for a moment. Let the double pendulum swing in your imagination, chaotic and precise, wild and lawful, free and determined, all at once. There is something almost comforting in this, if you approach it from the right angle. The unpredictability of the future is not a flaw in the universe. It is a consequence of the richness of its rules. The same sensitivity that makes weather forecasting impossible beyond 2 weeks is the sensitivity that makes ecosystems resilient. That allows evolution to explore vast spaces of biological possibility. That may even be part of what allows minds like yours to surprise themselves. Chaos is not the enemy of order. It is what order looks like when it is deep enough. We have been exploring systems whose unpredictability emerges from deterministic rules operating at the scale of everyday experience. But there is another layer of reality, deeper, stranger, and more fundamental, where unpredictability is not a practical limitation, but an irreducible feature of nature itself, where even perfect knowledge of the rules and the initial conditions cannot tell you what will happen next, where mathematics describes not what is, but only what might be. and assigns to each possibility nothing more definite than a probability. This is the world of quantum mechanics, and in that world, the mathematics is perfect. The predictions are the most precise in the history of science, and what those perfect, precise predictions describe is a reality built at its foundation, not from certainties but from chances. That is where we are going next, into the quantum, into the wave function and its collapse, into the place where mathematics meets the deepest uncertainty in nature and finds there not confusion, but extraordinary, almost eerie precision. Breathe slowly, let the chaos settle, and then follow me, gently, into the quantum world. Chapter 9. Quantum Probability, the Universe Rolls Dice. There is a particular kind of unsettling feeling that comes from learning something that cannot be unlearned, something that sits quietly in the back of your mind and refuses to leave. Not because it is frightening exactly, but because it permanently changes the texture of how you see the world. Quantum mechanics is full of such things, but perhaps none more so than this. At the most fundamental level of physical reality, beneath the atoms and the subatomic particles and the fields that fill the vacuum of space, the universe does not decide what will happen. It only decides how likely each possibility is, and the decision about which possibility actually occurs does not happen until something, we are still not entirely sure what, forces a choice. This is not a limitation of our instruments. It is not a consequence of our ignorance. It is not a problem that better technology will eventually solve. It is, as far as the most carefully tested and precisely verified theory in the history of human science can tell us, a fundamental feature of reality itself. The universe, at its deepest accessible level, is irreducibly probabilistic, and the mathematics that describes this probabilistic reality is among the most beautiful, most precise, and most conceptually disturbing mathematics ever written. To understand why this is so strange, it helps to remember what physics looked like before quantum mechanics. The classical picture, the world of Newton and Maxwell and Einstein's special relativity, was a world of definite quantities. A particle had a position, it had a velocity, it had energy. These properties were real. They were precise. Quantum mechanics took this picture apart completely. And it did so not because physicists wanted to, not because it fitted any philosophical preconception, but because experiment after experiment after experiment refused to fit the classical picture, no matter how cleverly it was adjusted or extended. The data demanded something new, and what was demanded was so strange that even the people who built quantum mechanics, Bohr, Heisenberg, Schrödinger, Dirac, Born, spent their careers arguing about what it actually meant. At the heart of quantum mechanics is a mathematical object called the wave function. Every quantum system, every particle, every atom, every molecule is described not by a list of definite properties, but by a wave function, usually denoted by the Greek letter psi. The wave function is a complex-valued mathematical function that encodes, in a precise way, the probability of finding the system in any particular state if you were to measure it. It is not a description of where the particle is. It is a description of where the particle might be, with what probability, if you were to look before you look. The particle does not have a definite position. It has a wave function, a superposition of all the positions it might occupy, weighted by their respective probabilities. The equation that governs how the wave function evolves through time is called the Schrödinger equation, formulated by the Austrian physicist Erwin Schrödinger in 1926. It is a deterministic equation, given the wave function at one moment. The Schrödinger equation tells you exactly what the wave function will be at any future moment. In this sense, quantum mechanics is perfectly deterministic. The wave function evolves in a smooth, predictable, mathematically well-defined way. There is nothing random about the evolution of the wave function. The randomness enters at a different point entirely. It enters when a measurement is made. When you interact with a quantum system in a way that counts as a measurement, when you force it to reveal a definite value for some property, the wave function does not smoothly evolve into a new wave function. It jumps. It collapses instantaneously from a superposition of many possible states into a single definite outcome. And the outcome that occurs is not determined by the wave function or by the Schrödinger equation. It is selected randomly, with probabilities given by the wave function. But the specific outcome is not determined by any prior cause that we can identify. It simply happens. One possibility is chosen from the distribution and the others vanish. This is called the measurement problem, and it is one of the deepest unresolved conceptual puzzles in all of physics. What counts as a measurement? What triggers the collapse of the wave function? Is the collapse a real physical process, or is it something else? These questions have been asked since the earliest days of quantum mechanics and have not been answered to universal satisfaction in the century since. Pause here. Let the strangeness of this settle. A theory that has been tested to extraordinary precision, that has produced predictions verified to more decimal places than any other theory in the history of science, contains at its center a process, the collapse of the wave function, that the theory itself does not fully explain. We know what the wave function does before measurement, and we know the probabilities of the outcomes after measurement. What happens in between, the actual selection of a definite outcome from the distribution of possibilities, is something the formalism of quantum mechanics describes but does not illuminate. The most successful physical theory ever devised has, at its heart, a mystery it cannot resolve. To make this concrete, let us spend a moment with the most famous thought experiment in all of quantum mechanics. Erwin Schrödinger himself devised it in 1935, not as a celebration of quantum weirdness, but as a reductio ad absurdum, an argument intended to highlight what he saw as the absurdity of the Copenhagen interpretation of quantum mechanics. The standard view promoted by Niels Bohr and his colleagues. Imagine a cat placed inside a sealed box. Inside the box, along with the cat, is a small amount of radioactive material, a Geiger counter, and a device connected to the Geiger counter that will release a lethal dose of poison if the Geiger counter detects a radioactive decay. The radioactive material has a 50% chance of decaying within 1 hour. After 1 hour, you have not yet opened the box. Is the cat alive or dead? In classical physics, the answer is obvious. The cat is either alive or dead. We simply do not know which until we open the box. Our ignorance does not affect the cat's state. The cat has a definite state. It is just hidden from us. But in quantum mechanics, the situation is more disturbing. The radioactive atom is a quantum system. Before we measure it, it is in a superposition of decayed and not decayed states. the Geiger counter, being coupled to the atom, becomes entangled with it. It too enters a superposition of having detected and not detected states. The Poison mechanism, coupled to the Geiger counter, enters a superposition of released and not released states, and the cat, coupled to the Poison mechanism, enters a superposition of dead and alive states. According to the strict formalism of quantum mechanics, before the box is opened, the cat is neither alive nor dead. It is in a superposition of both states simultaneously. The wave function of the cat includes both possibilities with equal weight. When you open the box and look inside, the wave function collapses. You find a definite outcome, alive or dead. But until that moment of observation, the quantum formalism says the cat was genuinely both, not just unknown, both. Schrödinger intended this as a demonstration that quantum mechanics could not be the complete picture, that something must happen at some scale to select a definite reality before macroscopic objects like cats enter absurd superpositions. What he produced instead was one of the most enduring illustrations of the deep strangeness of the quantum world, one that physicists are still debating today. Several interpretations of quantum mechanics have been proposed to make sense of this strangeness, each more conceptually radical than the last. The Copenhagen interpretation, the oldest and most widely taught, essentially says that the wave function is a tool for calculating probabilities and that asking what the system is doing between measurements is a meaningless question. Do not ask. Just calculate. This pragmatic stance produced a century of extraordinary physics, but it left many physicists deeply unsatisfied. Physics is supposed to describe what is happening, not just what we will measure. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a completely different approach. It says that the wave function never collapses. The Schrödinger equation always holds, completely and without exception. When a measurement is made, the universe does not select one outcome. It splits into multiple branches, one for each possible outcome. Each branch equally real, each containing observers who experience a definite result. In the Schrödinger's cat scenario, the universe branches into one in which the cat is alive and one in which it is dead. Both cats are real. Both exist. We experience only one branch, but the other is no less actual for being inaccessible to us. This interpretation has a beautiful mathematical economy. It requires no special collapse mechanism, no undefined measurement process, no division of the world into quantum systems and classical measuring devices. But it requires accepting that every quantum event in the history of the universe has generated branching worlds, an incomprehensibly vast proliferation of parallel realities, all equally. Whether this is the correct picture or not remains genuinely unknown. No experiment has yet been devised that can distinguish between the many worlds interpretation and several of its competitors. The mathematics is the same. The predictions are the same. What differs is the story we tell about what the mathematics means. And that story, the interpretation, is still being written. What is not in doubt is the extraordinary precision of the quantum mechanical predictions themselves. The most precisely tested prediction in all of physics is a quantum mechanical calculation of a quantity called the anomalous magnetic moment of the electron, a tiny correction to the magnetic properties of the electron arising from its interactions with the quantum vacuum, the theoretical prediction, derived from quantum electrodynamics. agrees with the experimental measurement to better than 1 part in a trillion to achieve comparable precision in everyday terms. You would need to measure the distance from London to New York to within a fraction of a millimeter. This is what quantum mechanics can do mathematically. This is the level of precision its equations achieve. And yet those same equations, applied to the question of what is actually happening when no one is looking, produce answers that range from deeply puzzling to frankly astonishing. The electron does not have a definite position between measurements. The cat is neither alive nor dead until observed. The universe may be splitting into parallel branches at every quantum event. The ground state of empty space seethes with energy. These are not the conclusions of sloppy thinking or inadequate mathematics. They are the conclusions that the most precise mathematics in human history forces upon us when we let us spend a moment with one more quantum phenomenon before we rest, because it deserves its own quiet contemplation. It is called quantum entanglement, and Einstein called it spooky action at a distance, a phrase he used dismissively, intending to highlight what he saw as an absurdity in quantum mechanics. But the absurdity turned out to be real. When two quantum particles interact in the right way, they can become entangled. Their wave functions become linked in such a way that the state of one cannot be described independently of the state of the other, regardless of the distance between them. Measure the state of one entangled particle, and the wave function of its partner collapses instantaneously to a correlated state, even if the partner is on the other side of the planet or the other side of the galaxy. The correlation is instantaneous. It does not diminish with distance. It cannot be used to transmit information faster than light. The outcome of each measurement is still random. So no signal can be encoded in it, but the correlation itself is real, verified in countless experiments, and it means that quantum particles separated by any distance remain, in a precise mathematical sense, a single system. The universe is, at the quantum level, non-local. The independence of distant things that we experience in everyday life is an approximation, a large-scale smoothing out of a deeper reality in which entanglement connects distant parts of the universe in ways that classical physics has no room for. We are all, at some level, entangled with everything we have ever interacted with, and they with us, in a web of quantum correlations that extends across the entire observable universe. Breathe slowly. Let the quantum world recede into the background of your awareness. The electron without a position. The cat in superposition. The universe branching at every quantum event. The entangled particles, correlated across the cosmos. All of it described by mathematics of extraordinary precision and beauty. All of it pointing toward a reality that is stranger, richer, and more deeply interconnected than the world our senses report. The mathematics of quantum mechanics operates at the smallest scales of physical reality, the scale of particles, atoms, the vacuum of space. But there is another domain where mathematics confronts the deepest questions of all, the scale of the universe itself, the scale at which the question is not what a particle is doing in a box, but what shape the entirety of space is, how it curves, whether it has edges, and what lies, if anything, beyond. That is the territory we are entering next. The topology of the universe, the mathematics of the shape of everything, a domain where the question is not just how the universe works, but what, in the most fundamental geometric sense, it is rest for a moment, and then When you are ready, follow me out to the largest possible scale, to the shape of all that exists. Chapter 10. The Topology of the Universe. What shape is everything? There is a question so large that it is difficult to know where to stand when you ask it. Not a question about what is inside the universe, about the particles and forces and fields that fill it, but a question about the universe itself as a geometric object, about its shape, about whether it has edges or boundaries, or whether it curves back on itself in some higher dimensional sense that our three-dimensional intuitions cannot directly perceive, about whether if you were to travel in a perfectly straight line in any direction for long enough, you would eventually find yourself back where you started, or whether you would travel forever outward and outward into an expanse that has no end. This is the question of the topology of the universe, and it is, in the most precise mathematical sense, still open. We do not know the answer. We have measurements, we have constraints, we have strong hints from the data that cosmology has accumulated over the past century. But the full geometric shape of the universe, the global topology of space itself, remains one of the deepest unsolved questions at the intersection of mathematics and physics. And the mathematics that has been developed to approach this question is among the most beautiful, most abstract, and most conceptually demanding in all of human intellectual history. To understand what topology is and why it matters for cosmology, we need to begin with a distinction that is fundamental but easy to overlook. The distinction between local geometry and global topology. Local geometry is about what space looks like in your immediate neighborhood. Is it flat, like a tabletop, where parallel lines stay parallel and the angles of a triangle add up to exactly 180 degrees? Is it positively curved, like the surface of a sphere, where parallel lines eventually converge and the angles of a triangle add up to more than 180 degrees? Or is it negatively curved, like the surface of a saddle, where parallel lines diverge and the angles of a triangle add up to less than 180 degrees? These questions about curvature are questions of local geometry, and they can, in principle, be answered by measurements made within a region of space, without reference to the larger structure of the whole. Global topology is a different kind of question entirely. It asks about the overall shape and connectedness of space, about what happens when you follow a straight line, not just for a short distance, but forever. Two spaces can have the same local geometry, but completely different global topologies. The surface of a cylinder, for example, is locally flat. A small region of it looks just like a piece of flat paper, with Euclidean geometry holding perfectly. But globally, the cylinder is not the same as a flat plane. If you travel in one direction on a cylinder, you eventually come back to where you started. The local and the global are different aspects of the same space, and knowing one does not automatically tell you the other. This distinction becomes crucial when we ask about the shape of the universe. Current cosmological measurements, particularly measurements of the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, strongly suggest that the universe is spatially flat, or very close to it. Parallel lines, extended over cosmological distances, appear to stay parallel. The geometry of space, on the largest scales we can measure, looks Euclidean, but flatness is a statement about local geometry. It says nothing definitive about global topology. A flat universe could extend infinitely in all directions, like an infinite flat plane, or it could be finite. curving back on itself in a way that is locally flat at every point, but globally connected, like a three-dimensional version of the surface of a torus. Let us pause on the torus for a moment, because it is the most accessible model of a finite flat space, and it opens up the intuition beautifully. A torus is the mathematical name for a shape like a donut, a surface generated by taking a rectangle and gluing its opposite edges together. Glue the top edge to the bottom edge, and you get a cylinder. Now glue the two circular ends of the cylinder together, and you get a torus. The resulting surface is locally flat. If you live on a torus and examine your immediate neighborhood, your geometry is Euclidean, but globally, the torus is finite. Travel far enough in one direction and you return to your starting point. Travel far enough in another direction and you also return. The space wraps around. It has no edges, no boundaries, no center. Now imagine the three-dimensional analog. Instead of gluing the opposite edges of a two-dimensional rectangle, imagine gluing the opposite faces of a three-dimensional cube. Glue the left face to the right face, the top face to the bottom face, the front face to the back face. The result is a mathematical object called a three-torus, a three-dimensional space that is locally Euclidean at every point but globally finite and periodic. If you were to stand inside a three-torus and look in any direction, you would eventually be looking at the back of your own head. Travel far enough in any direction and you return to your starting point. The universe would be finite but boundless. No walls, no edges, no place where space ends, but also not infinite. Could our universe have this topology? The honest answer is that we do not know, but it is a genuine possibility that cosmologists take seriously. If the universe were a three-torus of sufficient size, there would be a specific observational signature, light from distant galaxies, traveling in straight lines through the periodic space, would wrap around and arrive at us from multiple directions. We might see the same galaxy multiple times, at different ages, from different angles, without recognizing it as the same galaxy because we would be seeing it at different points in its history. The observable universe would contain repeating patterns, echoes of the same structures appearing in multiple directions in the sky, separated by distances corresponding to the size of the fundamental domain of the topology. Cosmologists have searched for these patterns in the cosmic microwave background and in the large-scale distribution of galaxies. So far, no definitive signature has been found, but the absence of a signature does not rule out a toroidal topology. It only constrains it. If the three-torus is much larger than the observable universe, the repeating patterns would be too far apart to detect. The topology of the universe could be finite and periodic, but on a scale so vast that the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, represents only a tiny fraction of the whole. We would be looking at a small patch of a much larger, possibly finite space, unable to see far enough to detect its global structure. There are other possible topologies, more exotic than the three-torus. The Poincaré dodecahedral space is a finite three-dimensional space constructed by identifying opposite faces of a dodecahedron, a 12-sided solid with pentagonal faces, with a specific twist. Its topology is more complex than the three-torus, with a smaller volume and a more intricate pattern of identifications. Some cosmologists in the early 2000s argued that features in the cosmic microwave background data were consistent with a Poincaré dodecahedral space. The claim was controversial and remains unresolved, but it illustrates the richness of the topological possibilities that mathematics makes available. Pause here for a moment. Let the strangeness of these possibilities settle. We are not talking about science fiction. We are talking about mathematically rigorous structures, studied and classified by topologists for over a century, that are consistent with everything we currently know about the physics of the universe. The universe might be a three-torus. It might be a Poincaré dodecahedral space. It might be some other finite compact manifold whose topology we have not yet considered, or it might be genuinely infinite, flat in all directions, extending forever, containing infinitely many galaxies and stars and, by implication, infinitely many copies of every possible arrangement of matter, including infinitely many copies of you. Reading these words in the quiet dark, that last possibility, the infinite flat universe, has its own deeply unsettling implications, ones that follow directly and unavoidably from the mathematics of infinity. If space is truly infinite, and if matter is distributed roughly uniformly throughout it on the largest scales, as observations suggest, then every possible configuration of matter must occur somewhere in that infinite space, simply because there are only finitely many ways to arrange a finite amount of matter in a finite region of space. And infinite space contains infinitely many such regions in an infinite universe. There are infinitely many planets, infinitely many stars, infinitely many galaxies, and inevitably, infinitely many regions of space that are, to within any specified degree of precision, identical to the region we inhabit. Infinitely many copies of the Earth, infinitely many copies of this moment, this night, this quiet, infinitely many versions of you, listening to the same words, breathing at the same pace, not in a mystical sense, not as a metaphor, as a straightforward mathematical consequence of infinite space and finite local configurations. Whether this constitutes a form of immortality, or a form of meaninglessness, or something else entirely, is a question philosophy must grapple with. Mathematics only delivers the implication. What you do with it is your own business. But let us come back to something closer to hand. Let us talk about the curvature of space in a more concrete way. Because general relativity, Einstein's theory of gravity, gives us a framework for thinking about how space curves that is both mathematically precise and deeply beautiful. In general relativity, gravity is not a force in the Newtonian sense. It is a curvature of space-time, the four-dimensional fabric that combines the three dimensions of space with the dimension of time, produced by the presence of mass and energy. Massive objects like stars and galaxies do not pull other objects toward them. They curve the space-time around them, and other objects simply follow the straightest possible paths through that curved space-time. What we experience as the gravitational pull of the Earth is simply the effect of living in a space-time that is curved by the Earth's mass, so that the straightest path through it, the path that a freely falling object follows, is a curve that brings us back to the surface. This framework allows us to ask not just about the local curvature of space near massive objects, but about the global curvature of the universe as a whole. The overall curvature is determined by the total energy content of the universe, the density of matter, radiation, dark matter, and dark energy, summed up and compared against a critical density, If the total density exactly equals the critical density, the universe is flat. If it exceeds the critical density, the universe is positively curved, like the surface of a hypersphere, a three-dimensional analog of the surface of a sphere, finite and without boundary, in which the sum of the angles of any triangle exceeds 180 degrees and parallel lines eventually converge. If the density falls below the critical density, the universe is negatively curved, like the three-dimensional analog of a saddle surface, in which the sum of the angles of any triangle falls below 180 degrees and parallel lines diverge. Current measurements place the density of the universe extraordinarily close to the critical value, within less than 1% by the most recent estimates. The universe appears to be flat, or very nearly so, but that measurement itself does not resolve the topological question, and it introduces another mystery. Why is the density so close to critical in the early universe? A density even slightly above critical would have led to a rapid recollapse, while a density even slightly below critical would have led to an expansion so rapid that galaxies could never have formed. The fact that the density is billions of years after the Big Bang, what topology does for us, ultimately, is this. It reminds us that the universe we can see, the observable universe, the sphere of space from which light has had time to reach us, is not necessarily the universe that exists. It may be a small sample, a local patch, a fragment of something whose global structure is completely inaccessible to direct observation. The shape of everything may be a question that, by its very nature, we are not positioned to answer from where we stand, like a being living on the surface of a vast torus, examining only the geometry of their immediate neighborhood, unable to travel far enough to detect the global topology of their world. We may be, cosmologically speaking, in exactly that position. Breathe slowly. Let the image of a finite but boundless space settle into the background of your awareness. A universe that curves back on itself somewhere beyond the horizon of observation. A cosmos in which traveling far enough in any direction might, against all intuition, bring you home. The mathematics allows it. The observations do not rule it out, and the question remains open, patient, thus. We have been thinking about the shape of the universe as it is. But the mathematics of modern physics does not stop at one universe. The equations we use to describe our universe, the same equations that describe quantum mechanics, that describe the Big Bang, that describe the behavior of fields in the very early cosmos, do not produce a single solution. They produce many. They produce, depending on how you count, infinitely many, and some physicists believe that each of those solutions corresponds to a real, existing universe, not metaphorically, not as a mathematical abstraction, as a physical reality, as concrete as the one you are lying in right now. That is the door we are approaching next, the multiverse. The mathematics that predicts too much, the equations that refuse to stop at one world and insist, with the same rigor that describes our own cosmos, on describing infinitely many others. Follow me gently into the space beyond spaces. Chapter 11. The Multiverse Equation, when math predicts too much. There is a particular discomfort that arises when a theory works too well, When the equations you have written down to describe one thing keep producing solutions that describe other things, things you did not ask for, things you did not expect, things that sit quietly at the edge of the mathematics and refuse to go away no matter how carefully you try to ignore them. This is the situation that modern physics finds itself in with respect to the multiverse. Not one physicist's eccentric speculation, not a fringe idea promoted by people who prefer imagination to rigor, but a conclusion that emerges, repeatedly and from multiple independent directions. From the same mathematical frameworks that have produced the most successful and precisely verified predictions in the history of science, the mathematics of our universe, it turns out, does not describe only our universe. It describes many, perhaps infinitely many. And the question of whether those other universes are real, whether the mathematics is pointing at something that actually exists or merely at solutions to equations that have no physical counterpart, is one of the most profound and most genuinely unresolved questions in all of contemporary physics and philosophy. To understand how this situation arose, we need to trace several threads that developed independently and converged over the course of the 20th century on the same unsettling destination. The first thread is quantum mechanics, which we explored in our last segment. Recall the measurement problem, the question of what happens when a quantum system in a superposition of states is measured, the Copenhagen interpretation, the standard view for most of the 20th century, said that measurement causes the wave function to collapse to a single definite outcome, with the other possibilities vanishing. But in 1957, a young Princeton doctoral student named Hugh Everett proposed a radically different answer. What if the wave function never collapses? What if the Schrödinger equation, the equation governing the evolution of the wave function, always holds, without exception, without any special collapse mechanism? If the wave function never collapses, then when a measurement is made, when a quantum system with two possible outcomes is observed, both outcomes occur. The universe does not select one and discard the other. Instead, the universe itself enters a superposition. One branch containing an observer who saw outcome A, another branch containing an observer who saw outcome B. Both branches are equally real. Both contain observers with genuine experiences of definite outcomes. Neither branch is aware of the other from the perspective of any individual observer. The measurement produced one result from the perspective of the mathematics. Both results occurred in different branches of a universe that is perpetually, irreversibly splitting. Everett called this the relative state formulation of quantum mechanics. It was later renamed the many worlds interpretation by the physicist Bryce DeWitt, who recognized its full implication that every quantum event in the history of the universe has generated branching worlds, and that the total number of branches, this is not a small claim. The many worlds interpretation, if correct, implies the existence of an almost inconceivably large number of parallel universes, all of them described by the same wave function, all of them obeying the same physical laws, all of them containing matter and energy, and in many cases, observers. The multiplication of worlds is not a feature that Everett added to make the theory more interesting. It is a direct consequence of taking the mathematics of quantum mechanics seriously and refusing to add any extra mechanism, like wave function collapse, that is not contained in the equations themselves. The many worlds are what you get when you let the mathematics speak for itself without interruption. Pause here for a moment. Let that breathe. The second thread leading to the multiverse comes not from quantum mechanics, but from cosmology. specifically from the theory of cosmic inflation that we touched on in our discussion of the shape of the universe. Inflation is the leading explanation for why the universe appears flat, why it is so uniform in temperature across regions that should never have been in causal contact, and why it contains the specific pattern of density fluctuations that seeded the formation of galaxies. The basic idea is that in the first tiny fraction of a second after the Big Bang, in a period lasting perhaps 10 to the power of negative 32 seconds, the universe underwent a period of exponential expansion, driven by a quantum field called the inflaton, that expanded space by a factor of at least 10 to the power of 26 in an almost unimaginably brief interval. Inflation solves the problems it was designed to solve with extraordinary elegance, but it also produces a consequence that its originators did not anticipate, and that many of them found deeply uncomfortable. The quantum field driving inflation is subject to quantum fluctuations, the same irreducible probabilistic variations that govern all quantum systems in different regions of space. These fluctuations cause inflation to end at different times. In most regions, inflation ends quickly, producing a universe like ours, with a specific density of matter and energy, specific physical constants, specific laws. But in other regions, the quantum fluctuations cause inflation to continue, and an inflating region of space expands so rapidly that it perpetually generates new inflating regions faster than inflation ends in existing ones. The result is a process called eternal inflation, a self-reproducing cosmos in which bubble universes are constantly nucleating out of an eternally inflating background, each bubble potentially with different physical properties, different constants, different laws. This is the inflationary multiverse, and unlike the many worlds multiverse, which arises from quantum mechanics alone, the inflationary multiverse arises from the combination of quantum mechanics with the classical field theory of inflation. It is not a philosophical extrapolation or a speculative add-on. It is a direct mathematical consequence of the most successful theory of cosmic origins we currently possess. The same equations that account for the flatness of the universe, the uniformity of the cosmic microwave background, and the distribution of galaxies on the largest scale. The third thread is perhaps the most philosophically audacious of all. It comes from the work of the physicist and cosmologist Max Tegmark, who has spent decades developing and defending what he calls the mathematical universe hypothesis. Tegmark's argument begins with a relatively modest observation that the universe appears to be described by mathematics with extraordinary precision, that physical reality seems to be, at its deepest level, mathematical in structure. From this starting point, Tegmark takes a single additional step that transforms the observation into a radical metaphysical claim. He argues that the universe is not merely described by mathematics, it is mathematics. Physical existence and mathematical existence are the same thing. Any mathematical structure that is consistent and well-defined exists as a physical reality somewhere in the ultimate ensemble of all possible mathematical structures. If Tegmark is right, then the multiverse is not just the many worlds of quantum mechanics, or the bubble universes of eternal inflation. It is the totality of all possible mathematical structures, every consistent set of equations, every coherent formal system, every well-defined mathematical universe that can be described without self-contradiction. This is the most expansive multiverse of all. Not just universes with different physical constants or different initial conditions, but universes with entirely different laws of physics, different numbers of dimensions, different relationships between cause and effect, different logics underlying their structure. Every mathematical world that can be coherently described exists somewhere. This proposal is, to put it gently, not universally accepted. Many physicists find it too metaphysically extravagant, too far removed from empirical testability, too close to the kind of speculative philosophy that physics has historically tried to avoid. The standard criterion for a scientific theory is that it makes predictions that can, in principle, be tested if every possible universe exists. Then our observation that we live in this particular universe provides no constraint on the theory. Any observation is consistent with it, which means the theory predicts nothing specific for many scientists. A theory that predicts everything is indistinguishable from a theory that predicts nothing. But here is the counter-argument that Tegmark and others have offered, and it is worth sitting with carefully. The reason we observe the specific physical laws we do, the specific values of the constants of nature, the specific structure of quantum field theory, the specific geometry of space-time, may not be that these are the only possible laws, or the most fundamental, or the ones selected by some deeper principle. It may be that we observe them simply because they are the laws that permit the existence of observers. A universe with different constants might not permit the formation of stars, or complex chemistry, or life, in a vast ensemble of universes with varying properties. Observers can only exist in the subset of universes whose properties are compatible with the existence of observers. This is the anthropic principle, the observation that any universe we observe must, by definition, be compatible with our existence, and the fine-tuning of the physical constants, the extraordinary precision with which the values of things like the strength of gravity, the mass of the electron, the cosmological constant appear to be adjusted to permit the existence of complex structure and life, has long been one of the most puzzling features of our universe, in a single universe. This fine-tuning demands an explanation. Why are the constants what they are? What set them? Is there some deeper principle from which they can be derived? In a multiverse, the question dissolves. The constants are what they are in our universe, because our universe is the subset of the multiverse where observers like us can exist. Other universes have different constants, and in most of them, no one is asking the question. Whether this constitutes a genuine explanation or a sophisticated evasion of the question is something physicists and philosophers continue to argue about with genuine passion and without resolution. The multiverse is, in this sense, deeply controversial, not because the mathematics that produces it is uncertain, it is not, but because the question of what the mathematics means, whether its solutions correspond to physical realities or merely to mathematical possibilities, is one that physics alone cannot answer. It bleeds into philosophy, into the theory of knowledge, into the question of what we mean by existence and reality and truth. Take a slow breath. Let the immensity of these ideas settle gently around you. There is something both vertiginous and strangely liberating about the multiverse, if you approach it in the right spirit. If the many worlds interpretation is correct, then every decision you have ever made, every path not taken, every moment of hesitation or courage or failure or grace, all of them are real somewhere in the branching tree of quantum histories. The version of you that took the other road exists. the conversation you almost had happen, the life you sometimes wonder about is being lived, not as a comforting fantasy, but as a mathematical consequence of taking quantum mechanics seriously. If the inflationary multiverse is real, then our universe, with its specific laws, its particular constants, its 13.8 billion years of history leading to this precise moment, is one bubble among perhaps infinitely many, each one a complete cosmos with its own story, its own stars, its own silences. We are not the only universe. We may not even be a typical one. We are simply the one in which the conditions for wondering about such things have been met. And if Tegmark's mathematical universe hypothesis is correct, then existence is not a special property that some mathematical structures have and others lack. Existence is what mathematical structures do. Every consistent mathematical world is real. Every coherent set of equations describes something that actually exists. The universe is not a physical thing that happens to be describable by mathematics. It is mathematics, all the way down, with no remainder. These are not comfortable ideas. They are not designed to be. They are the ideas that fall out of the mathematics when you follow it honestly, without flinching, past the point where intuition can follow, and they raise, with enormous force, a question that none of them can answer. A question that is in some ways more fundamental than all the physics and all the mathematics we have been exploring tonight. Not what universes exist, or how many, or what laws they obey, but why anything exists at all, why there is something rather than nothing, why the mathematics runs, rather than sitting silent in a void of pure logical possibility. That is the question we are carrying with us into the next segment. The oldest question in philosophy, the question that mathematics can approach, can illuminate, can hold up to the light and turn in its hands but cannot answer. The question that may, in a precise and verifiable sense, be unanswerable from any position inside the universe that contains it. Rest here for a moment. Let the multiverse recede into the background, vast and quiet, each of its infinite branches unfolding in perfect mathematical silence, and then follow me forward into the deepest silence of all. Chapter 12. The Unreasonable Silence. Why is there something rather than nothing? There is a question that has no comfortable place to rest. It is not a question that belongs exclusively to mathematics, or to physics, or to philosophy, though all three have reached toward it with their best tools and found those tools, at the last moment, falling just short. It is a question that arrives most naturally in the quiet hours, in the spaces between thoughts, in the particular stillness that descends when the ordinary business of the mind finally grows tired and falls silent. It is a question so fundamental, so stripped of assumption, that it is almost impossible to think about directly for very long without a kind of mental vertigo setting in. And it is this: why is there something rather than nothing? Not why is there this universe rather than a different one? Not why do the physical constants have the values they have? Or why does mathematics describe reality with such precision? Or why did the Big Bang occur at all? Those questions, difficult as they are, at least have the form of questions that science and mathematics can approach. They ask about the properties of something that exists, but the deepest question asks something more radical. It asks why existence itself, why anything at all, rather than the complete, total, absolute absence of everything. No matter, no energy, no space, no time, no mathematics, no laws of physics, no possibility, no potential, nothing in the most unqualified and total sense of the word. This question was formulated most sharply by the philosopher Gottfried Wilhelm Leibniz in 1714 in a short essay called The Principles of Nature and Grace. Leibniz asked it simply and directly, why is there something rather than nothing? And recognized immediately that it could not be answered by pointing to anything that exists, because any existing thing merely pushes the question back a level. If the universe exists, you can ask why the universe exists. If there is a God who created the universe, you can ask why God exists. If there is a mathematical structure that underlies physical reality, you can ask why that mathematical structure exists rather than no structure at all. Every answer that invokes something existing to explain existence simply relocates the mystery without dissolving it. Leibniz himself believed the answer lay in God, a necessarily existing being whose non-existence would be a logical contradiction, and from whose nature all contingent existence flows. But this answer, whatever its theological merits, does not resolve the mathematical and philosophical dimensions of the question. It simply asserts that one particular entity, God, has its existence built into its definition in a way that nothing else does. Whether such a being is coherent, whether necessary existence is even a meaningful concept, whether the question it answers is the same question Leibniz asked, has been debated by philosophers for 3 centuries without resolution. Modern physics has approached the question from a different direction, and the results are both illuminating and, in their own way, deeply humbling. The most important contribution physics makes to this question comes from quantum mechanics, and specifically from the behavior of what physicists call the quantum vacuum. In classical physics, empty space is genuinely empty. A perfect vacuum contains nothing, no particles, no energy, no fields, but quantum mechanics, through the Heisenberg uncertainty principle, tells a completely different story. The uncertainty principle states that certain pairs of physical quantities, position and momentum, energy and time, cannot both be precisely defined simultaneously. The more precisely you know one, the less precisely you can know the other, and this applies not just to particles but to the fields that fill space. A quantum field permeating all of space cannot have a precise energy value of exactly 0 at every point simultaneously, because 0 is a perfectly precise value, and quantum mechanics forbids perfect precision. The field must fluctuate, even in its lowest energy state, even in what we call the vacuum. A quantum field is in constant, irreducible motion, flickering with energy fluctuations that are not a result of anything disturbing the field but an intrinsic feature of its quantum nature. These are called vacuum fluctuations or quantum fluctuations, and they are real. They have measurable consequences. The Casimir effect, which we explored when discussing the sum that equals negative 1/12, is one such consequence. The Lamb shift in the energy levels of hydrogen atoms is another. Vacuum fluctuations are not theoretical abstractions. They are physically real processes with experimentally verified effects. The cosmologist Lawrence Krauss wrote a controversial book arguing precisely this, that the universe could have arisen from nothing through quantum processes, making the question of why there is something rather than nothing answerable within physics. But the philosopher David Albert, among others, pointed out the fatal flaw in this argument, the quantum vacuum. however empty it appears, is not nothing. It is a physical state governed by the laws of quantum field theory, existing within a mathematical framework, obeying equations. It is a very particular kind of something, a something with a great deal of structure built into it. Explaining how the universe arose from the quantum vacuum explains a great deal, but it does not explain why there is a quantum vacuum rather than nothing at all. The question simply retreats one level deeper. Pause here, take a long, slow breath. Let us approach the question from the direction of mathematics, because mathematics offers a framework for thinking about it that is different from, and in some ways more penetrating than, the frameworks of physics or theology. Consider mathematical necessity. Some truths are contingent. They happen to be true but could, in some sense, have been otherwise. The Earth happens to orbit the Sun. Water happens to be composed of hydrogen and oxygen. These are facts about the particular universe we inhabit, not logical necessities. They could have been different without generating any contradiction, but other truths are necessary. They could not be otherwise without contradiction. 2 + 2 = 4 in every possible universe, because its negation is logically incoherent. This suggests a possible approach to the question of why there is something rather than nothing. Perhaps nothing, absolute, total, complete nothingness, is not actually a coherent possibility. Perhaps the existence of mathematical truths is itself a form of existence that cannot be switched off, that requires no physical substrate, that is not contingent on the existence of any universe or any matter or any mind to think about it. In this view, the reason there is something rather than nothing is that nothingness itself is mathematically incoherent, that a state of truly complete absence would require the non-existence of mathematical truths, which is impossible because mathematical truths are necessary rather than contingent. This is the germ of Max Tegmark's mathematical universe hypothesis, which we explored in our discussion of the multiverse. If mathematical structures exist necessarily, if their existence is not contingent on any physical universe but is built into the very structure of logic, and if existence is what mathematical structures do, then the question of why there is something rather than nothing dissolves. There was never a possibility of nothing. Mathematical existence is the bedrock of all possible existence, and mathematical existence cannot be absent without contradiction. This is a genuinely beautiful argument. It has the quality of the best mathematical proofs, a sense of inevitability, of ideas fitting together with a precision that feels almost like discovery rather than invention. But it does not fully close the question, because even granting that mathematical structures exist necessarily, even granting that their existence is not this is the question that Stephen Hawking identified as the deepest in all of cosmology. In A Brief History of Time, he asked what it is that breathes fire into the equations and makes a universe for them to describe. The equations of physics are mathematical structures. They have the kind of necessary existence we have been discussing. But they could, in principle, exist as pure mathematics, as abstract truths about abstract objects, without any corresponding physical reality. Something makes them physical. Something makes them real in the sense that there are actual particles following them, actual fields obeying them, an actual universe instantiating them, and that something, the fire that breathes life into the equations, is not itself described by the equations. It lies outside the mathematics, in a space that mathematics cannot reach. This is, in the deepest possible sense, a Gödelian situation. Recall that Gödel's incompleteness theorem showed that no formal system powerful enough to describe arithmetic can prove its own consistency from within itself. The system cannot pull itself up by its own bootstraps. The ultimate foundation of the system lies outside the system, and here, at the question of existence itself, we encounter the same structure. The universe is described by mathematics. The mathematics is necessarily true. But why the mathematics is instantiated, why there is a physical universe rather than merely a mathematical structure with no physical reality, is a question that lies outside the system, outside the mathematics, outside everything that exists. Let us approach the question from one more angle, because it has been considered from many directions, and each direction illuminates a different facet of its depth. The philosopher Derek Parfit, one of the most careful and rigorous thinkers to take this question seriously, proposed a classification of possible answers. He distinguished between what he called minimalist possibilities, the idea that the simplest possible reality is the most natural, and what he called maximalist possibilities, the idea that all possible realities exist. Nothingness, on the minimalist view, would be the natural default, the simplest possible state, and the existence of something would require an explanation. On the maximalist view, everything that is possible exists, and the existence of our particular universe requires no more explanation than does the existence of any mathematical truth. Parfit himself found neither option fully satisfying. Nothingness is, in his view, not obviously simpler than something. The concept of nothingness is itself a kind of something, a specific and well-defined state that requires its own justification. And the maximalist view, while coherent, raises the question of why all possibilities are realized rather than some of them, which is itself a form of the original question, he concluded, with characteristic intellectual honesty, that the question of why there is something rather than nothing may be permanently beyond our ability to answer, not because of any practical limitation, but because any possible answer to it will invoke something whose existence requires its own explanation. This is the deepest and most honest stopping point that philosophy has found. The question does not have an answer that closes it. Every answer opens it again at a deeper level. The regress does not terminate, and at some point, at the very bottom of the question, where the last explanatory resource has been exhausted, there is silence. Not the silence of ignorance, not the silence of a question that has not yet been investigated carefully enough, but the silence of a question that may be, in principle, beyond the reach of any intelligence operating from within the reality it is trying to explain. This is what we mean when we say that Gödel's incompleteness applies not just to formal mathematical systems, but to existence itself. The universe is the system. The question of why the system exists is the unprovable true statement. It can be formulated. It can be recognized as genuine. It cannot be proven from within. It cannot be answered from inside. And yet, and this is perhaps the most important thing to carry with you into the quiet of the night, the fact that the question cannot be answered does not make it meaningless. It makes it the most meaningful question there is. It is the question that lies beneath every other question, every scientific investigation, every mathematical proof. Every philosophical argument ultimately rests on the brute fact that something exists rather than nothing, a fact that cannot be explained but only marveled at. The entire enterprise of human understanding, every equation, every theorem, every experiment, every moment of genuine comprehension takes place against the backdrop of this foundational mystery. We think because, and that something, whatever it is, however it came to be, wherever its deepest explanation lies, has, after 13.8 billion years, produced beings capable of asking why it is here. That may not be an answer, but it is, in its own way, extraordinary. Breathe slowly. Let the silence of the question hold you for a moment. Not the silence of an empty room, but the silence of a question so large that all of mathematics and physics and philosophy can fit inside it and still not fill it up. We have been traveling through the deep interior of mathematical mystery, from the atoms of arithmetic to the shape of the cosmos to the reason for existence itself. And now, as we begin the final passages of tonight's journey, we turn from the very large to something closer to home, something that appears not in the equations of physics or the theorems of pure mathematics, but in the most ordinary numbers of everyday life, something hiding in plain sight in every financial record, every census, every scientific data set, a mathematical signature so universal and so unexpected that it can distinguish the real world from a human imitation of it. We are heading toward Benford's law, toward the suspicious first digit, toward the discovery that the universe signs its work and that the signature, once you know how to read it, is surprisingly hard to forge. Chapter 13, Benford's Law, the suspicious first digit. Imagine you are sitting at a desk, late at night, with a long list of numbers in front of you. The numbers represent financial transactions, payments made, invoices issued, amounts transferred from one account to another over the course of a year. There are thousands of them. They range from tiny amounts to very large ones. Some are round numbers, some are oddly precise, some end in zeros, and some end in seemingly random digits. To the untrained eye, the list looks like nothing more than what it is, a long, unremarkable column of figures. The kind of data that fills spreadsheets in every office in the world, the kind that most people glance at briefly and quickly look away from. But a forensic accountant, sitting down with that same list and knowing what to look for, might notice something subtle, something statistical, something that has nothing to do with the specific values of any individual transaction, but everything to do with the distribution of a single digit, the very first digit of each number. And what they might find if the person who compiled that list fabricated some of the numbers rather than recording real transactions is that the first digits do not follow a pattern that occurs naturally, that the list looks in a specific and quantifiable mathematical sense too human, too evenly distributed, too much like what a person imagining random numbers would produce, rather than what the world actually generates when left to its own devices. This is the forensic application of one of the most surprising and counterintuitive results in all of applied mathematics. It is called Benford's Law, and once you understand it, you will never look at a list of numbers quite the same way again. Benford's law makes a claim that sounds, at first encounter, almost absurd. It says that in many naturally occurring collections of numbers, populations of cities, lengths of rivers, stock market prices, physical constants, the surface areas of lakes, the heights of mountains, the number of Twitter followers of randomly selected accounts, the values of mathematical sequences, the sizes of files on a computer hard drive, the leading digit. The very first non-zero digit of each number is not distributed uniformly across the 9 possible values from 1 to 9. It is distributed according to a precise, predictable logarithmic pattern. The digit 1 appears as the leading digit approximately 30.1% of the time. The digit 2 appears approximately 17.6% of the time. 3 appears 12.5% of the time. 4 appears 9.7% of the time. And the probability decreases smoothly and continuously all the way down to 9, which appears as the leading digit only about 4.6% of the time. 1 appears as the first digit nearly 7 times more often than 9. In any large, naturally occurring data set, roughly 1 in 3 numbers begins with the digit 1. If you have never encountered this before, your immediate reaction is probably skepticism. Why would 1 appear more often than 2, or 2 more often than 5? If numbers are distributed randomly, shouldn't each leading digit appear equally often, roughly 11% of the time? That is certainly what intuition suggests. It is also what most people, when asked to generate a list of random numbers, unconsciously produce: a roughly uniform distribution of leading digits. And it is precisely this intuitive The history of the discovery is itself worth savoring. The first person to notice this pattern was not a statistician or a mathematician, but an astronomer named Simon Newcomb. In 1881, Newcomb was working with logarithm tables, thick books of pre-computed values that scientists of that era used constantly for calculation in the days before electronic computers. He noticed something peculiar about the physical condition of the book. The early pages, the pages containing logarithms of numbers beginning with 1, were significantly more worn and dirty than the later pages. They had been consulted more frequently. Scientists, in their daily calculations, were looking up numbers beginning with 1 far more often than numbers beginning with 8 or 9. Newcomb published a short paper noting this observation and deriving the logarithmic distribution that would explain it. His paper was largely ignored. The mathematical community of 1881 had other things on its mind, and a curious observation about the wear patterns of logarithm tables did not seem urgent enough to pursue. The observation was independently rediscovered 57 years later, in 1938, by a physicist named Frank Benford, who worked as an engineer at General Electric. Benford was more thorough than Newcomb. He compiled data from 20 different sources: river lengths, population figures, physical constants, numbers appearing in newspaper articles, molecular weights, baseball statistics, numbers from Reader's Digest articles, and found that in every data set, the leading digit distribution followed the same logarithmic pattern. He published his findings in a paper titled The Law of Anomalous Numbers, and this time the observation caught the attention of the scientific community. But understanding why Benford's law holds, constructing a genuine mathematical explanation for this deeply counterintuitive pattern, took considerably longer. The most satisfying explanation was developed over the latter half of the 20th century, and it involves a beautiful insight about the nature of scale. Consider what it means for a data set to span several orders of magnitude, to contain numbers ranging, say, from 1 to 1 million. Such a data set covers a range of values so large that the numbers are best understood not on a linear scale but on a logarithmic one. On a linear scale, the distance from 1 to 2 is the same as the distance from 100 to 101, or from 999,000 to 1 million. But on a logarithmic scale, the scale on which human perception of magnitude actually operates, and on which the structure of many natural phenomena is organized, the distance from 1 to 2 is the same as the distance from 2 to 4, or from 4 to 8, or from any number to its double. The logarithmic scale reflects multiplicative structure rather than additive structure, and multiplicative structure is exactly what governs growth, scaling, and the distribution of quantities across orders of magnitude in the natural world. On a logarithmic scale, the numbers beginning with 1 occupy the interval from 1 to 2, a range that corresponds to a logarithmic width of the logarithm of 2, approximately 0.301. The numbers beginning with 2 occupy the interval from 2 to 3, a logarithmic width of the logarithm of 3 halves, approximately 0.176. The numbers beginning with 3 occupy the interval from 3 to 4, a logarithmic width of the logarithm of 4/3, approximately 0.125, and so on, down to none. This is the deep reason why Benford's law holds. It is not a mysterious cosmic preference for the digit 1. It is a consequence of the fact that many natural data sets span multiple orders of magnitude, and quantities that span multiple orders of magnitude tend to be distributed logarithmically rather than linearly. The law is, in this sense, a statement about the geometry of the number line as experienced by naturally occurring data, a statement that the logarithmic scale, not the linear scale, is the natural habitat of quantities that grow, multiply, and scale across the wide range of values that the physical and biological and economic world generates. There is a beautiful and slightly eerie additional property of Benford's law that deserves its own moment of reflection. It is scale invariant and base invariant. If a data set obeys Benford's law in one system of units, in meters, say, it will continue to obey Benford's law if you convert every measurement to feet or to centimeters or to light years. The distribution of leading digits is unchanged by multiplication by any constant. This is exactly what you would expect of a logarithmic distribution, because multiplying all values by a constant shifts the logarithms by a fixed amount without changing their relative distribution. Scale invariance is a deep mathematical symmetry, and Benford's law is one of its most elegant expressions in empirical data. Pause here for a moment. Take a slow breath. Now let us talk about the forensic application, because it is one of the most striking examples of pure mathematics having direct, practical, real-world consequences. When human beings fabricate numbers, when they invent financial transactions, falsify accounting records, manufacture experimental data, or produce fraudulent statistics, they tend to distribute the leading digits of their invented numbers roughly, uniformly. This is not because they are being careless. It is because uniform distribution is what their intuition tells them random data should look like. When we imagine a random number, we are roughly equally likely to start with any digit. We do not naturally generate numbers whose first digits follow a logarithmic distribution, because the logarithmic distribution is counterintuitive and our number-generating intuitions are not calibrated to it. Real financial data, on the other hand, does follow Benford's law, because financial transactions reflect the same multiplicative scale-spanning dynamics that govern other naturally occurring data sets. Company revenues, expenses, payments, and account balances tend to be distributed logarithmically across orders of magnitude. Their leading digits follow the Benford distribution, and when a fraudster invents numbers that follow a uniform first-digit distribution instead, the deviation from Benford's law becomes a statistical signal, quiet, invisible to casual inspection, but detectable to anyone who knows to look for it. This technique is called Benford's law analysis, or digital analysis, and it has been used in real fraud investigations since the 1990s, when the statistician Mark Nigrini demonstrated its effectiveness in detecting fabricated financial data. It has since been the applications extend beyond forensics. Benford's law has been used to verify the authenticity of large scientific datasets, to detect anomalies in macroeconomic statistics reported by national governments, to identify potentially manipulated election results in countries where independent verification is difficult, and to check the internal consistency of computer simulations. Wherever large collections of numbers are generated by natural processes, physical, biological, economic, social, Benford's law provides a baseline expectation against which deviations signal something worth investigating. It is, in a very real sense, a mathematical fingerprint of the natural world, and perhaps the most remarkable thing about it is this. The universe generates numbers that prefer to begin with 1. Not because of any mystical significance of that digit, not because of any preference encoded in the laws of physics, but because of the deep mathematical relationship between multiplicative scaling and logarithmic distribution that governs how quantities of all kinds, from the sizes of stars to the amounts of financial transactions to the populations of cities, are spread across the orders of magnitude that natural processes produce. The world leaves a mathematical signature in its numbers, and that signature is surprisingly easy to read once you know the alphabet. There is something quietly profound about the fact that a pattern so universal, so deeply embedded in the structure of naturally occurring data, went unnoticed for most of human history. That Simon Newcomb noticed it in the Where on library pages in 1881, that Frank Benford confirmed it across 20 datasets in 1938, that the mathematical explanation required most of the 20th century to fully develop. Let that thought settle gently as you breathe. The numbers around you, in the world, in the accounts that govern daily life, in the data that describes the physical cosmos, are not neutral. They carry a pattern, a signature, a quiet mathematical truth that distinguishes the real from the fabricated, the natural from the invented, the world as it is from the world as a human mind imagines it should be. We have been exploring patterns that are hidden, patterns that are universal, patterns that connect the abstract world of mathematics to the concrete world of physical reality. But there is one more category of mathematical pattern we have not yet visited, patterns that are not hidden at all, but that reveal, with stark and unavoidable clarity, the fundamental limits of what any system, however powerful, can know about itself. Patterns that are not about the world outside the mind, but about the structure of reasoning itself, about the boundaries of computation, about what it means to think and what thinking cannot do, no matter how far it is extended. We are approaching the halting problem. We are approaching the limits that Alan Turing found in 1936, before computers existed, limits that apply to every computer ever built and every computer that ever will be built, and that may apply in a deep and unresolved way to the minds that built them. Rest for a moment, and then follow me into the final corridors of tonight's journey. Chapter 14, The Halting Problem, Limits of What Can Be Known. There is a question that sounds, when you first hear it, like something a computer science professor might ask on the first day of an introductory course, a warm-up question, a gentle exercise in logical thinking before the real material begins. The question is this: given a computer program and a specific input, can you always determine in advance whether the program will eventually finish running and produce an output, or whether it will run forever, looping endlessly, never arriving at a result? Take a moment to think about it. It seems, at first, like it ought to be solvable. Programs are precise. They follow exact rules. They do exactly what they are told to do, in exactly the order they are told to do it. Surely, with sufficient cleverness, sufficient analysis, sufficient mathematical sophistication, you could examine any program and its input and determine, before running it, whether it would eventually stop. You might need to think carefully. You might need powerful tools. But there does not seem to be any fundamental reason why the answer should be out of reach. And yet it is, not merely difficult, not merely practically infeasible for very complex programs, fundamentally, provably, mathematically impossible. No algorithm exists that can solve this problem for all possible programs and all possible inputs. No computer, however powerful, however cleverly programmed, can answer this question in general. This is the halting problem, and its proof. Constructed by the British mathematician and logician Alan Turing in 1936. A decade before the first programmable electronic computer was built, is one of the most profound and to fully appreciate what Turing did and why it matters so deeply. We need to understand the context in which he was working. Turing was a 24-year-old graduate student at Cambridge when he wrote the paper that introduced what we now call the Turing machine and proved the undecidability of the halting problem. He was working, as Gödel had been 5 years earlier, in the shadow of David Hilbert's program, the grand project to place all of mathematics on a complete and consistent foundation. Hilbert had asked, among other things, a question he called the Entscheidungsproblem, the decision problem. He wanted to know whether there existed a definite procedure, an algorithm, in modern terminology, that could take any mathematical statement as input and determine, in a finite number of steps, whether that statement was provable within a given formal system. The question mattered enormously. If such a procedure existed, it would mean that mathematics was, in principle, fully mechanizable. Every mathematical question would have a definite answer that could be computed by following a fixed set of rules. Mathematics would be not just consistent and complete, the dream that Gödel had already shattered, but decidable. Every truth would be reachable by a finite procedure. Turing answered Hilbert's decision problem with a definitive no, and to do so, he first had to invent a precise mathematical model of what it means to compute something. This model is the Turing machine. A Turing machine is an abstract device of extraordinary simplicity. It consists of an infinitely long tape divided into cells, each cell containing a symbol from a finite alphabet. A read-write head moves along the tape, reading the symbol in the current cell, and based on that symbol and the machine's current internal state, doing three things: writing a new symbol in the current cell, moving the head one step left or right, and transitioning to a new internal state. The machine continues operating according to this simple rule until it enters a designated halting state, at which point it stops. That is all. No memory beyond the tape, no parallel processing, no random access, just a head moving along a tape, reading and writing symbols, changing state. This device, in its extreme simplicity, turns out to be capable of computing anything that any computer, past, present, or future, can compute. The Church-Turing thesis, one of the foundational principles of computer science, states that any function computable by any effective procedure can be computed by a Turing machine. The entire power of modern computing, every algorithm, every program, every piece of software ever written is captured, in principle, by the behavior of this simple abstract device moving along an infinite tape, the smartphone in your pocket, the servers that power the internet, the supercomputers that model climate and simulate particle physics. All of them are, in a precise mathematical sense, Turing machines with finite tape. Now Turing asked, can a Turing machine determine, for any other Turing machine and any input, whether that machine will eventually halt? Can compute? And here he deployed a proof of devastating elegance. Using the same self-referential structure that Gödel had used 5 years earlier in his Incompleteness theorems. The argument is a proof by contradiction. It assumes the thing it wants to disprove, derives a logical impossibility from that assumption, and concludes that the assumption must be false. Suppose, for the sake of argument, that a halting oracle exists, a program, call it H, that takes any program P and any input I and correctly determines, in a finite number of steps, whether P will halt when run on I. H always gives the correct answer. H never fails. H is the solution to the halting problem. Now use H to construct a new program. Call it D for diagonal, echoing Cantor's diagonal argument, which we explored when discussing the different sizes of infinity. D takes any program P as input, calls H to determine whether P halts when run on itself, when P is used as both the program and the input, and then does the opposite of what H predicts. If H says P will halt when run on P, then D loops forever. If H says P will not halt when run on P, then D halts immediately. Now ask what happens when D is run on itself, when D is used as both the program and the input. Call H to determine whether D halts when run on D. If H says D halts, then D, by its construction, loops forever, contradicting H's prediction. If H says D does not halt, then D, by its construction, halts immediately, again contradicting H's prediction. In both cases, the argument is so clean, so precise, so utterly unambiguous that it is almost shocking. It does not say that we have not yet found an algorithm to solve the halting problem. It does not say that the algorithm is too complex to construct. It says, with mathematical certainty, that no such algorithm can exist. Not now, not in the future, not with any technology, not with any amount of cleverness or computational power. The halting problem is not just unsolved, it is unsolvable, and it is not alone. Turing's result opened a floodgate. In the decades following his 1936 paper, mathematicians and computer scientists discovered that the halting problem is only the first and most famous member of a vast family of undecidable problems. Problems that are precisely and rigorously formulated, that have definite correct answers for every specific instance, but for which no general algorithm exists that correctly solves every instance. The question of whether a given program will ever output a particular string is undecidable. The question of whether two programs compute the same function is undecidable. Many questions about the long-term behavior of programs, questions that seem like they should be answerable by careful analysis, turn out to be undecidable in general. Rice's theorem, proved by the mathematician Henry Gordon Rice in 1951, establishes a sweeping and somewhat stunning generalization. It states that for any non-trivial property of the behavior of programs, any property that some programs have and some programs lack, where the property concerns what the connection to Gödel's incompleteness theorems is not accidental, it is deep. Gödel and Turing were working on the same fundamental problem from different angles. Gödel from the direction of mathematical logic, Turing from the direction of computation. What they both discovered, using different tools and different formalisms, is the same underlying truth. Self-reference, applied to sufficiently powerful systems, generates questions that those systems cannot answer about themselves. A formal system powerful enough to describe arithmetic cannot prove its own consistency. A computational system powerful enough to simulate any computation cannot determine, for arbitrary programs, whether they will halt. The two results are not merely analogous, they are, in a precise mathematical sense, equivalent. The undecidability of the halting problem and the incompleteness of arithmetic are two manifestations of the same deep structural limitation. This structural limitation has a name in computer science. It is called uncomputability. A problem is uncomputable if no algorithm can solve it in general, and the boundary between computable and uncomputable problems is one of the most important and most carefully studied frontiers in all of theoretical computer science. On one side of the boundary lie the problems that computation can solve: sorting, searching, optimizing, simulating, predicting within computable domains. On the other side lie the problems that computation cannot solve, the halting problem, questions about the long-term behavior of programs, certain problems in number theory, certain questions about the structure of formal systems. Now let us ask the question that makes this relevant not just to computer scientists, but the mathematician and physicist Roger Penrose argued in his books The Emperor's New Mind and Shadows of the Mind that the answer reveals something important about consciousness. Penrose observed that human mathematicians seem to be able to recognize Gödelian truths, statements that are true but unprovable within a given formal system, as true, despite the fact that no algorithm within that system can prove them. He argued that this ability demonstrates that human mathematical cognition is not entirely computational, that the mind does something that no Turing machine can do, and that this something involves a form of insight or understanding that transcends mechanical rule following. The argument is controversial and has been challenged by many philosophers and cognitive scientists. The most common objection is that Penrose's argument proves too much, that recognizing a Gödelian statement as true requires knowing that the formal system in question is consistent, which is itself an assumption that cannot be proven from within the system. A human mathematician who claims to recognize Gödelian truths as true is, on this view, relying on an intuition about consistency that is not itself infallible, and that may itself be subject to Gödelian limitations at a higher level. But the deeper question that Penrose raises, whether human cognition has genuine computational limits analogous to the halting problem, remains genuinely open. We do not know, in any rigorous sense, the computational structure of human thought. We do not know whether the brain is a Turing-complete system. whether consciousness introduces any computational capabilities beyond Turing computability, or whether what we can say with confidence is this. The halting problem establishes that there are well-defined, precisely formulated questions about the behavior of programs, questions that have definite, correct answers for every specific case, that no algorithmic process can answer in general. If you build a system powerful enough to simulate any computation, that system will necessarily be blind to certain questions about its own behavior, self-knowledge, at the computational level, has hard limits, not soft limits, not practical limits, hard, mathematical, proven, permanent limits. And here is the thought that lingers longest in the quiet after Turing's proof has been absorbed. Every computer ever built is a Turing machine. Every algorithm ever written is a Turing computable function. Every program, every app, every piece of software that has ever run on any device anywhere in the world operates within the computational framework that Turing defined in 1936, and is therefore subject to the limitations that Turing proved in that same paper. The devices that now permeate every aspect of modern life, that navigate our cars, manage our finances, filter our information, power our communications, and increasingly make decisions that affect our lives, all of them are operating within a framework that has known, proven, mathematical blind spots built into its very foundations. We have built a civilization on computation, and computation, at its core, cannot answer certain questions about itself, cannot verify its own behavior in all cases, cannot determine for this is not a crisis, it is a fact, a mathematical fact of the same kind as the irrationality of the square root of 2, or the transcendence of pi, or the incompleteness of arithmetic. It is a boundary of knowledge, as real and as permanent as any physical boundary, built not into the limits of our technology, but into the structure of logic itself. Breathe slowly. Let the weight of that settle gently. Turing himself is worth a final moment of quiet reflection, because his life carried its own kind of tragic beauty. He was one of the most brilliant minds of the 20th century. During the Second World War, he was central to the British effort to break the German Enigma cipher, a contribution that historians estimate shortened the war by at least 2 years and saved millions of lives. He laid the mathematical foundations of computer science, proposed a test for machine intelligence that bears his name and is still debated today, and made fundamental contributions to mathematical biology in the final years of his life. He was, by any measure, among the most consequential thinkers of his era. In 1952, he was prosecuted by the British government for gross indecency, the legal term at the time for homosexuality, and subjected to chemical castration as a condition of avoiding imprisonment. He died in 1954 at the age of 41 from cyanide poisoning. The coroner's verdict was suicide. Whether it was deliberate or accidental has been debated since, and will likely never be conclusively resolved. He was granted a royal pardon by the British government in 2013, posthumously, 59 years after his death. The man who proved that there are things computation cannot know died in circumstances that speak to a different kind of limit, the limit of a society's capacity to recognize the humanity of the person standing before it. There is something in that parallel that resists easy articulation, but that deserves, in the quiet of this late hour, a moment of acknowledgement. We have been traveling throughout this long night, through the outer reaches of mathematical knowledge, through incompleteness and infinity, through chaos and quantum uncertainty, through the shape of the cosmos and the silence at the heart of existence. And now, in this segment, we have arrived at something that draws all those threads together. The limits of knowledge are not accidents or temporary gaps waiting to be filled. They are structural features of any system powerful enough to ask deep questions about itself. They are the price of sufficient complexity. They are, in Gödel's terms, the unprovable truths that every rich enough system necessarily contains. And perhaps that is not something to be troubled by. Perhaps the limits of what can be known are, in their own way, as beautiful as the knowledge itself, because they mean that the questions never run out, that the horizon is always there, that no matter how far computation and mathematics and physics and philosophy advance, there will always be something beyond the reach of the current system, something that requires a new perspective, a new framework, a new way of standing in relation to the questions. There is always more. The limits guarantee it. We are approaching the final segment of tonight's journey now. One more door, and behind it lies the question that is, in some ways, the most intimate of all the questions we have explored, not about numbers or programs or the shape of the universe, but about the one thing in all of mathematics and physics that remains most deeply, most stubbornly, most beautifully unexplained. The thing that is doing the exploring right now, in this quiet moment, in the space behind your eyes, consciousness, the hard problem, the pattern that finds you. Rest for just a moment, and then, one final time, follow me. Chapter 15. The Pattern That Finds You. Mathematics and the Nature of Consciousness. We have traveled a long way tonight, through the atoms of arithmetic and the mysteries of prime numbers, through the infinite hierarchy of infinities and the sum that should not exist, through the golden spirals of living things and the chaos hidden inside perfect order, through the quantum uncertainty at the heart of physical reality and the topological shape of the cosmos itself, through the multiverse that mathematics insists on predicting and the ancient silence at the center of the question of existence, through the forgery-detecting signatures of Benford's law and the computational limits that Turing proved can never be overcome. We have followed the thread of mathematics through some of the strangest and most beautiful territories the human mind has ever mapped. And now, at the end of this long, quiet journey, we arrive at the territory that is simultaneously the most familiar and the most mysterious of all. We arrive at the question that mathematics, for all its extraordinary power and reach, has not yet managed to touch in any satisfying way. The question that physics, neuroscience, philosophy, and cognitive science have circled for decades without finding a center. The question that is not about anything out there, not about numbers or particles or the shape of space, but about the fact that there is an in here at all. Why are you conscious? Why is there something it is like to be you? This is the hard problem of consciousness, a phrase coined by the philosopher David Chalmers in a landmark 1995 paper that crystallized a distinction that many thinkers had felt but few had articulated so precisely. Chalmers drew a line between what he called the easy problems of consciousness and the hard problem. The easy problems, and he acknowledged that calling them easy was something of a misnomer. since they are in fact extraordinarily difficult by ordinary scientific standards, are questions about the functional and behavioral aspects of mind. How does the brain integrate information from different sensory sources? How does it focus attention on some stimuli and ignore others? How does it control behavior in response to its environment? How does it generate reports about its own internal states? These questions are difficult, but they are, in principle, answerable by the methods of neuroscience and cognitive science. They ask how the brain does what it does, how it processes, integrates, responds, reports, and progress, real and substantial progress, is being made on all of them. The hard problem is different in kind, not just degree. It is the question of why any of this processing is accompanied by experience. Why? When the neurons in your visual cortex fire in response to light of a particular wavelength, do you not merely process the information that a certain wavelength is present? Why do you see red? Why is there a felt quality to the experience, a redness of red, a what it is like to see that color that seems to be over and above any functional description of what the neurons are doing? Why does the information processing in your brain feel like anything at all, rather than proceeding in the dark? This gap, the gap between the objective, third-person description of neural processing and the subjective, first-person reality of experience, is what Chalmers called the explanatory gap, and it is the reason the problem is hard. Not hard in the way that a difficult calculation is hard, or the way that a complex experiment is hard to design. Hard in the sense that the standard tools of scientific explanation, reduction, mechanism, causal analysis, mathematical modeling, seem, when applied to this question, to leave something out. They explain the mechanism, they do not explain the experience. Pause here. Take a long, slow breath. Feel what it is like to breathe, not the mechanics of it, the expansion of the diaphragm, the rush of air through the trachea, the inflation of the alveoli, the exchange of oxygen and carbon dioxide across the capillary walls. Those things are happening, and they are real, and they are described with precision by biology and physics. But there is also something else happening, the felt quality of the breath, the coolness of the air entering, the gentle release of the exhalation, the subtle shift in awareness that comes with a slow, deliberate breath. That felt quality is what we are talking about. That is the hard problem, made personal and immediate and undeniable. Now, let us look at what mathematics and physics have tried to do with this problem, because the attempts are themselves fascinating, and the partial answers they have produced are worth dwelling on. The most mathematically developed theory of consciousness currently on the table is called integrated information theory, developed by the neuroscientist Giulio Tononi in the early 2000s and refined substantially in the years since. Integrated information theory begins with a philosophical move. Instead of asking what physical systems give rise to consciousness, it asks what consciousness is and what physical properties a system must have in order to instantiate it. Tononi's starting point is the observation that consciousness has two fundamental properties. It is highly differentiated. Each conscious experience is specific, distinct from all other possible experiences, carrying a precise and particular content. And it is highly integrated. Each conscious experience is unified, a single whole rather than a collection of separate parts. You do not experience the left half of your visual field independently of the right half. You do not experience sound and color as separate streams of information that happen to co-occur. You experience a unified, integrated scene. Tononi proposed that consciousness just is integrated information, that the degree of consciousness of any system is identical to the degree to which the system integrates information in a way that cannot be fully reduced to the sum of its parts. He introduced a mathematical measure called phi, not the golden ratio we encountered earlier, but a different phi. The implications of this framework are striking and, depending on your philosophical priors, either deeply illuminating or deeply troubling. A simple thermostat, with its minimal information integration, has phi very close to zero. It is barely conscious, if at all. A human brain, with its extraordinarily rich patterns of information integration, has a very high phi. It is highly conscious. But the framework also implies that consciousness is not unique to biological systems, or even to systems that look anything like brains. Any system with sufficiently high phi, any system that integrates information in the right way, will be conscious to some degree. This makes integrated information theory a form of panpsychism, the view that consciousness, or at least its precursor, is a fundamental and ubiquitous feature of the physical world, present to some degree in all information processing systems. Panpsychism is an ancient philosophical position associated with thinkers as diverse as Leibniz, Spinoza, and William James, and it has experienced a remarkable revival in recent decades among both philosophers and neuroscientists. The appeal is understandable. If consciousness arises from integrated information, and if information processing is a widespread feature of physical systems, then consciousness is not a mysterious anomaly, a strange exception to the otherwise unconscious physical world, but a natural consequence of the structure of information itself, more or less present wherever information is more or less integrated. But integrated information theory has serious problems. The most pressing is computational. Calculating phi, there is also a deeper philosophical objection. Integrated information theory tells us which physical systems have high phi. It does not tell us why high phi should be accompanied by experience. It does not explain why integrated information feels like anything. It maps the territory of consciousness with mathematical precision, but does not close the explanatory gap. Why does phi correspond to experience? Why is it not the case that systems with high phi simply process information more richly, without any inner felt quality? The hard problem in this life is not so much solved as relocated, moved from the question of which physical processes give rise to consciousness to the question of why integrated information should feel like anything at all. The second major mathematical framework for consciousness is called global workspace theory, developed by the cognitive neuroscientist Bernard Baars and given a more neural and mathematical form by the neuroscientist Stanislas Dehaene and colleagues. Global workspace theory proposes that consciousness arises when information is broadcast widely across the brain through a global workspace, a network of interconnected areas that allows information processed locally in specialized regions to become globally available to many different cognitive processes simultaneously. On this view, consciousness is the global availability of information, the state in which a particular piece of information has been amplified, broadcast, and made accessible to the wide range of cognitive processes that constitute thinking, planning, speaking, remembering, and acting. Global workspace theory has strong empirical support. The neural signatures of, but again, the hard problem persists. Global workspace theory explains when information is globally available and how that global availability is implemented in the brain. It does not explain why global availability should be accompanied by experience. Why does it feel like something when information enters the global workspace? Why does the broadcasting of information create an inner light rather than simply making the information more widely accessible in the dark? Take another slow breath. Feel the quiet of this late hour. Feel the awareness that is. Right now, attending to these words, following their thread, noticing the ideas as they arrive. That awareness, so intimate, so immediate, so undeniably present, is what neither integrated information theory nor global workspace theory has yet fully explained. They have mapped its correlates with impressive precision. They have not touched its essence. There is a third possibility that deserves careful attention. Not because it solves the problem, but because it reframes it in a way that feels, to many thinkers, like genuine progress. This is the view associated most prominently with the philosopher and cognitive scientist Daniel Dennett, who argues that the hard problem of consciousness is not a genuine problem at all, that it is a philosophical illusion generated by the particular way human beings represent their own mental states to themselves. Dennett's position, which he has developed across several decades and multiple books, is that when we introspect, when we turn our attention inward and report on our conscious experiences, we are not accessing some inner theater in which a unified conscious experience is displayed. We are generating a narrative, a story that the brain tells about itself, assembled from the outputs of many parallel, distributed processes, none of which is itself conscious in the way the narrative claims. The feeling that there is something it is like to see red, on this view, is not a datum that demands explanation. It is a representation, a way of modeling one's own states that is itself a product of evolution and cognitive development. There is no explanatory gap because there is no inner experience that is separate from the physical process. The experience just is the processing, reported from the inside. This position is deeply controversial and has been called, by its critics, the view that simply denies the existence of the phenomenon it purports to explain. If you feel with absolute certainty that there is something it is like to be you right now, and most people do feel this with absolute certainty, then a theory that tells you this feeling is itself a kind of illusion seems to be explaining away rather than explaining. The debate between Dennett's deflationary view and Chalmers' hard problem view is one of the most sustained and unresolved disputes in contemporary philosophy of mind. Both positions have brilliant defenders. Neither has achieved anything close to consensus. What mathematics contributes to this debate is, in a sense, something structural rather than something, and perhaps that is the most important thing to say about consciousness in the context of everything we have explored tonight. We have seen, over the course of this long journey, that mathematics has limits. Gödel showed that mathematics contains truths it cannot prove. Turing showed that computation contains questions it cannot answer. Cantor showed that infinity has depths that no finite process can exhaust. Chaos theory showed that deterministic systems can be permanently unpredictable. Quantum mechanics showed that certainty at the foundation of physical reality. gives way to probability. And now, here, at the question of consciousness, we find that the mathematical description of physical processes, however complete, however precise, leaves something out: the inner light, the felt quality, the what it is like. Perhaps consciousness is the universe's way of experiencing itself from the inside. Perhaps the same mathematical laws that govern the behavior of matter and energy and information, operating in systems of sufficient complexity and integration, give rise not merely to more complex behavior, but to something qualitatively new, to perspective, to experience, to the felt quality of being a particular point of view within the larger whole. Perhaps the hard problem is hard because it marks the boundary between the third-person description of the universe and the first-person reality of being in it. And perhaps no amount of third-person mathematics can ever fully capture the first-person reality, because first-person reality is not the kind of thing that third-person descriptions are built to contain. Or perhaps Dennett is right. And what seems like an explanatory gap we do not know. That is the honest answer. We do not know whether consciousness is fundamental or emergent, whether it is ubiquitous or rare, whether it requires biology or merely information integration, whether it can be fully explained by physics and mathematics, or whether it represents something genuinely beyond their reach. We do not know whether you are the only conscious being in the universe, or whether consciousness is everywhere, flickering at different levels of intensity in every information processing system, from the simplest organism to the most complex brain. We do not know whether the mathematics that describes your neural activity captures everything about your experience, or whether something essential escapes the description. What we do know, what cannot be doubted, even in the middle of the deepest philosophical skepticism, is that you are here, that something is happening right now in the space behind these words, that the journey we have taken tonight through the prime numbers and the fractals, through the infinite infinities and the collapsing wave functions, through the shape of the cosmos and the silence at the heart of existence, has been experienced, has been felt, has passed through the filter of a conscious mind and emerged as something more than information, as meaning, as wonder, as the particular quality of attention that human beings bring to questions that are larger than they can answer. You are a mathematical object in the sense that you are made of matter governed by mathematical laws, but you are also something that mathematical laws, so far, have not explained: a perspective, a witness, an awareness that is not reducible, at least not yet, and that, the fact that you exist, that you wonder, that you are here in the quiet of this late hour following the thread of these ideas through the dark. That is the most unsettling pattern of all, not because it is frightening, but because it is irreducibly real in a way that no abstract mathematical object can be, because it is yours, because it is now, because no amount of equations, however beautiful and precise, can reach all the way to the inside of it. Let your breathing slow. Let the ideas dissolve gently, one by one. The prime numbers are still out there, scattered along their infinite road. Gödel's unprovable truths still hover at the edge of every formal system. The wave function is still collapsing somewhere. Into the world you will wake up to tomorrow. The universe is still unfolding in all its mathematical splendor and all its irreducible mystery, in every direction at once. And you, aware, wondering, breathing, here, a part of that unfolding, not an observer standing outside it, not a mind floating free of the mathematics that governs matter, but a pattern within the pattern, a structure that the universe has produced in order, perhaps, to know itself, to wonder about itself, to lie awake in the quiet hours and feel the strangeness of existence and find that strangeness beautiful. Rest now. Let the numbers go. Let the theorems dissolve. Let the questions that have no answers settle into the background like the hum of distant stars, present but not demanding, real but not urgent. You have thought about large things tonight. You have sat with mysteries that the greatest minds in history have not resolved, and you have done so in the most intimate possible setting, alone, in the quiet, in the particular stillness that arrives when the world grows dark and the mind grows soft and the distance between mathematics and meaning begins to close. The patterns will be here when you return. They always are. Patient, precise, endlessly strange, and somehow inexplicably beautiful. Sleep well.